In this one, we are going to be creating a custom machine learning model from scratch. We will train it, and then we'll turn it into a REST API. We're going to be doing this by using Keras, which is the Python machine learning library. We'll also be using FastAPI, which is a really popular API framework for Python. And then we're going to go ahead and integrate all of these things, store it all into a Cassandra database using the managed AstraDB service. Let's go ahead and jump right in. I wanted to thank DataStax for sponsoring this series. So if you don't already have an account on there, check out this link right here as a way to show your support as well. Thanks so much. Let's go ahead and take a look at the demo. Now, if you look here, this is the local FastAPI project working, and this is a streaming response in FastAPI from our AstraDB. This is actually really, really cool. So it's literally all of our new data set. It's not our old data set, it's just everything that's coming in new. Next thing, we actually can take a look at this using a service called Ngrok. This is how we expose it to the outside world from our local machine. It's really easy to do. It's just a simple setup, and then we just run it. The final thing is actually a deployed version of this. So this is it right here. This IP address is probably not going to be available when you're looking at it, but the general idea is all three of these things have the same data, right? Which is really, really cool. And this is just showing all of the inferences that have been done, right? So like this right here, this is awesome. That was what was being predicted on, and it gave a 86% chance that this was ham, as in not spam. And so we can go through this whole thing and check it out, or we can actually take a look at a notebook on Google Colab to see how we actually run this in real time. So we import requests. We have one of those endpoints here, like I'm using the Ngrok one to start out, and I can put in my query here. So this is not spam, probably, right? And so I run that, and it'll give me the query back, of course. It gives me the label that it thinks it is, and it gives me the confidence for that. Another one would be actually spam. So let's say, for instance, get a new phone at, a huge discount. So I purposely did some weird errors there, or weird numbers there. But now we've got this weird text coming through. Looks like spam just from looking at it, but we can now see that it's an 83% confidence that it is spam. That's pretty cool if you ask me. Next, of course, is the data set itself. So we can actually go through here and go line by line and get every single piece from this new data set, which would include this weird new thing that we just did, right? So this line right here should also be in there. If I do a quick search for it, there it is right there in that data set. So now using the production version one, it's the same thing. It's not going to be any different. You can actually use that in production, and it's going to be just as fast, if not faster than going through Ngrok. Probably faster than Ngrok because of the server that we end up using. And then, of course, we can go line by line on that production grade one as well. So that's the demo of it working. Now, the entire code, all of it is in two places on GitHub. One is the actual production version that I'm using, which is this repo right here on our GitHub account. And these will be linked in the description too, so you don't have to search for them. The other one is the API course itself. So the actual code that we do in this entire series, that's this reference right here. They're not going to be that much different, but the biggest difference will be the actual AI as an API. That one will continue to improve off of the video with a number of things that I'm probably not going to cover in this series, including the terraforming of all of this. This is a whole new sort of topic that we'd want to cover in another time. So anyways, so that is the demo. Let me know if you have questions. Otherwise, let's take a look at the requirements to do well in this series. Now, before we jump in, I'm going to assume that you have experience with Python already. So if you don't have experience with Python, definitely check out my 30 Days of Python series. The idea here is you need to be really comfortable with variables, functions, classes, and really just sort of like cleaning up data, maybe have some experience with Python requests. A lot of those things are done in 30 Days of Python. So check that one out. It's on my website at cfe.sh/projects. It's also on my YouTube channel as a playlist. So if you look for cfe.sh and then /YouTube, you will actually find my YouTube channel, and then you'll be able to find this playlist as well. So let me know if you have any questions on what the requirements are. They're pretty straightforward. If you have a really solid foundation in Python, great. And even if you don't have that solid of a foundation, I'm going to show you how to do a lot of these things step by step. So if you have to rewatch any videos because maybe I'm going too fast for your experience level, that's okay. That is something that a lot of people do all the time. I do it as well. Sometimes I'm watching something and I'm learning something new. I got to rewind it several times before I get it done. And then of course, as I mentioned with the demo, all of our code is on GitHub. So if you go to github.com/coding4entrepreneurs or more simply cfe.sh/GitHub, this will take you to our primary repositories. And if you look for AI as an API, that will be a really solid reference for you for this project going forward. Now, if you need the actual course reference itself, then you're going to want to look for the one called AI as an API course reference. It's just slightly different, but it's going to match exactly what's happening in the course, where the AI as an API one is going to be updated over time. So let's go ahead and jump into our project and our series now. All right, so in this one, we're going to go ahead and configure our project using Python and VSCode. So I'm going to assume that you have both of these installed. I'm going to be using Python 3.9, but you want to have at least Python 3.6 and above. And then also VSCode, open source, definitely not Visual Studio, but Visual Studio Code is what you want to download and open. So once you open it, you'll see something like this. We just need to create our project. And so we open up the Explorer, or you can go to File and Add Folder to Workspace, either one. Basically opening up a folder. I'm going to navigate to where I want to save this project. I put it in my dev folder, which I created next to my user itself. And inside of a folder, I'm going to call AI-API. So I'll go ahead and add. And in my case, I actually already have a file in here, which includes a requirements.txt. So for those of you who are incredibly familiar with this process, these are the requirements. So feel free to install these and skip the rest of this video if you know what to do as far as creating a virtual environment. Okay, so now that I have this workspace folder, I'm going to go ahead and save this workspace as whatever you want to call it. I'm going to call it AI-API. Okay, simple enough. Now I'm going to go ahead and go to the terminal, and I'm going to open up a new terminal here. Now it's probably a good idea to learn this actual shortcut to opening this. Just like that. I use that shortcut all of the time. Okay, so again, I'm using Python 3 and it's 3.9.7. Now, whenever you open up this terminal, it's going to bring you right into the root of your project folder, as in where this code workspace ends up being, which is really, really nice, I think. Okay, cool. So now that we've got this, I'm going to go ahead and do Python 3-m venv period and just create a virtual environment. Now, if you're on Windows, you probably won't have to type out 3. You'll probably type out Python-m. But of course, I'm on a Mac, and that gives me the wrong version of Python. And of course, if you are on a Mac or a Linux, you can type out different versions of Python as well and see all of that stuff. I'm really hoping that's sort of repetitive information that you've already heard before. But now that we have this virtual environment, I have all of these new files here. I'm going to go ahead and activate it with source bin/activate. Of course, if you're on Windows, it's ./scripts/activate, just like that. But the way you know that it is activated is the name of the folder will be in parentheses like this. And then also if you do Python-v, no matter what system you're on, it's going to be the Python version that you initialized this virtual environment with. So now what I want to do is just do pip install-r requirements.txt. Now it is very common for this to not work given your system. So if that doesn't work, you could always open up a new terminal window. And again, it's in the same root. Then we want to source bin/activate. What you can do is you can run python-m pip install whatever, right? That's just another quick way to call any of the Python modules. In fact, this is what you'll want to use if any of these modules don't end up working, if any of the actual command line commands don't work. So the other part of this is TensorFlow itself, right? This is a big package. So if you are not ready to have TensorFlow installed on your local system, just go ahead and remove that. That's okay. No big deal at this point. When we actually bring it into production, it's going to be a lot bigger of a deal. At some point, you'll probably want to have TensorFlow working on your system. I do highly, highly recommend it. Now, while this is finishing up, what I will say is we are going to be using Jupyter Notebooks a good amount to write a few things with the code. This is mainly to really see how to experiment with creating a data set or cleaning a data set, but also experimenting with training an AI. Now, most of you, I'm going to assume, do not have a GPU on your local machine. So we're actually not going to be using the local machine for our AI training, which we'll talk about when we get there. But Jupyter Notebooks are a way to write interactive code, essentially. So I can just write some code, test some things out really quickly, which is why we have this in here. This is not a production dependency. The production dependencies look a little bit more like that, right? So when we actually bring this live, when the world can see it, we won't need Jupyter and Pandas in there. Those are just really development tools to get to the point where we can actually have a production AI using FastAPI's API service, or creating FastAPI API service. So I'm gonna let this finish installing and then we'll come back. Right, so all of my dependencies ended up finishing. So I can actually run pip freeze or simply python-m pip freeze and see everything that installed. The key one for us is TensorFlow 2.6. If a newer version of TensorFlow comes out, then there's a possibility we might need to use this older version of TensorFlow 2.6. But let me know in the comments if that's the case. So now that we have these dependencies, let's go ahead and take a look at a Jupyter Notebook by just typing out Jupyter Notebook. And again, if you're not able to do that, just run this command, and that should actually open up the Jupyter Notebook server. And so it will open up your browser and you'll be able to write a bunch of notebooks in here. So we'll go ahead and create a folder and just call this folder in here. Let's actually zoom in a little bit. Let's call this folder notebooks. And I'm just going to give you a very basic notebook here. And I'm just going to say print. Let's go ahead and print out hello world and hit Shift Enter to run it. Okay, so it's just a really easy way to run code inline. And as you see this number incrementing, that's the number of times that I actually used that cell. Now I will say VSCode does have the ability to run notebooks as well, but this is not something I'm going to be using here, right? So this is the VSCode version of a Jupyter Notebook. By all means, if you want to, go ahead. I'm going to go ahead and close out Jupyter Notebooks and delete everything I have, including the folder itself. Okay, so this is the baseline configuration for our project. Be sure to make sure that all of these requirements are in requirements.txt. That is standard. The other thing is you also might want to use Git. So let's go ahead and close out our Jupyter Notebook with Control-C. That's what I'm pressing many, many times. So Git is a version control system, right? So if I did git init, this will actually track my code. Now, if you've actually never used Git before, then I don't recommend trying to force this in here. When we need to use the Git code itself, the code that we will need for production, I'll show you what you need to do for that. For now, though, we're just going to use git init. And so I'm going to go ahead and also do a Python git ignore file and add this in as well. Usually on GitHub, there's a really good one. So I'm going to go ahead and grab that. And we're going to go ahead and make it in the root of our project with .gitignore and paste this in here. Save that, and then this number should no longer be 5,000, but maybe a few. In my case, I don't want bin, include, or lib, any of those things either, which, you know, some projects do want them, which is why that get ignored. It doesn't have them yet, at least. Okay, so we save that, and now we'll go ahead and also git include and share here. Great, so really our project doesn't have a whole lot, and if we do git status, we can see that. These are the things that will be tracked from our code or could be tracked. And if I add them, they will be. So initial commit. Cool. All right. So with all of the Git related things, if you actually go to cfe.sh/github, this URL will have all of our code that we ever produce. And if you look for AI as an API, this will be the final working production ready code once it is polished. This is not the code that we're going to be working off of in our videos. Now, in our videos, I will have another repo for that, which I'll definitely have linked somewhere in the descriptions. But the general idea is the code itself. This is code that I've been experimenting with to ensure that a real production AI as an API does work with a bunch of other configuration we're just not going to cover yet. But it is a good reference for the things that we might need in general for this project, because I'm not going to be diverting too much from what you see on GitHub at this point. In order to create our AI algorithm, we have to start with a data set. Now, in our case, we're going to be using a data set from the UCI, the University of California at Irvine, their machine learning repository. They have all kinds of open source data sets that we can use in our projects. Now, there's a good chance that it's going to look different by the time you get here, but the idea is we want to download one of their data sets, and then we're going to clean it up and get it ready for machine learning. So that's what we'll do for the next few parts. Now, I will say a lot of this is going to be based off of the guides that we have on the AI as an API repository. So if you go to that on GitHub, you can actually see a number of these guides that we'll be going through. Now, the reason I recommend that you stick with me if you aren't that familiar with this process is so that you can learn the thought process behind what makes those guides versus just running those guides. But by all means, do it however you want to do it, and I will explain how I think about this right now. So going into the UCI machine learning repository, we're going to do a quick search for spam. Right, so the algorithm that I want to build is a spam detector, basically. Like, I'm going to send in a string of text, and it's going to tell me if it's spam or not. That's it. It's fairly simple of a problem, but still a pretty useful one itself. Okay, so if we come in here and do the search, we see that there's a number of spam-like data sets. Okay, so the ones I'm going to be using is the spam SMS dataset and the YouTube spam collection dataset. So I'm going to go ahead and open these things up. And this is what they look like right now. So if I go to download and hit the data folder on both of these, what I'll see is a zip file listed here. Now, if you want to think about this not programmatically, you would actually just download the zip files into a folder, and then you could manually unzip them, right? By all means, go ahead and do that if that's the method you want to go about doing this. My method, though, is to automate this as much as possible. I don't want to have to think about this. And also, when I start experimenting with building the actual AI model, I want a really easy way to grab these data set anywhere without extra configuration. In other words, I want to automate it. Okay, so for this, I'm going to go ahead and create a Jupyter notebook. And we're just going to be focusing on the downloading portion of this inside of a Jupyter notebook. So we'll go ahead and create a new folder, and I'm going to rename it to MBS, and inside of here, we'll go ahead and create a new file here, and I'm just going to call it one download and datasets. Cool. So what is it that I'm trying to download? This file right here. Okay, so I'm going to go ahead and copy the link to it, and I'll paste it in here as a string. Okay, that's simple enough, right? So this is the spam or SMS spam zip. All right. And so there's a command that we can use on our machine called curl, right? And so curl, if we go to, like, let's say our terminal window or PowerShell, depending on what you're on, and just type out curl, you'll see something like this. Not, command not found, basically, or some other error. So curl is going to allow us to open up this page and do something with it. So I can actually run curl inside of Jupyter using that URL. We don't need it in quotes at all. And then we can just put an out file as in like spam-dataset.zip. Can run that, and that will actually download that zip file or whatever is on that URL, and it will output it to spam-dataset.zip. And so with that, I can actually go into my project here, open up that notebooks folder again, and I see spam dataset in here. This, of course, is not where I want to keep this zip file. Personally, I want to keep things organized, so I'm going to go ahead and delete that. And I want to just restructure how I'm going to go about downloading this. Now, of course, this is going to take some Python to do it. I'm going to use import pathlib, the actual pathlib library that's built into Python itself, and we're going to declare our base directory from pathlib. It's just pathlib.path, and we'll just go ahead and do resolve. Okay, and let's go ahead and see that result. There we go. So in my case, it's going into my notebooks folder. I actually want the root of my project, so that would just be .parent. That gives me the root of my project. So to actually use this variable inside of Jupyter on a curl call, which again, that's a terminal call, especially using the exclamation mark before it makes it a terminal call, I can actually use $ and that variable with a trailing slash. Notice there's not a trailing slash here. So when I do that and run it, let's go see where it goes now. So now, if I scroll to the bottom, I see it in the root of my project. It's no longer in that notebooks folder. Now it's here. Okay. So this may or may not be review for some of you. I'm going to go ahead and delete that file. But the idea here is we want to be systematic about where we download things. And so with that in mind, I'm going to go ahead and add my dataset dir, and this is going to be my base directory, and I'll just call it datasets. And then we'll go ahead and do our imports, or let's call it our zip file actually. Let's go zips dir, and this is going to be my datasets dir, zips, and zips. What I want to do is I want to make sure that that exists by just doing make dir and exist okay being true and parents being true as well. So that will create all of the actual folders I want. So datasets and zips, all of those folders are in there now. And so what I want to do is then get it to that path. Okay, so zips dir, and right here, let's go ahead and do that. And there it is. Cool. A little bit better. Now in my case, in my get_ignore file, I'm actually going to ignore that. So datasets and zips. I don't actually want to commit that data because again, I'm going to be extracting it from here. And the goal of, well, these actual notebooks would be to download them, combine them, and make them usable. So the final result will probably commit into our repo. But the actual current state of it, we don't need to commit at all. But we can actually make this a little bit better. And that is this right here. I actually do want to have my spam SMS zip path. And that's sort of a arbitrary name there. But it's going to be based off of this right here. And there we go. So this is now where I want to save it, and we'll just put it next to that $ there. And again, it's not necessarily going to, we need to run that and run this again. It didn't really change anything, right? It did override that file, but the idea here is it's still the same exact thing. Now, the reason I actually declare a path for it is so I can unzip it then in a moment. But before I actually unzip it, let's get the other YouTube spam zip link. And so that one is, the other link here. So I'm going to go ahead and copy this, paste that in there. Okay. So much like this one, I'll just go ahead and create another one and call this spam YouTube zip path. And this time is the YouTube dataset. Actually, the spam dataset should probably be SMS spam and simply YouTube spam. We want to be, well, very clear as to what's going on here. Okay, so this curl command, I'm just going to add one more to it, just right below it. And of course, it's going to have to be the correct URL, which I do have these URLs here. I just haven't been using them. So let's go ahead and use them now with the $ there and $ here. And let's get rid of the spaces if you have them. Okay. And of course, the spam path itself. Great. And so now it should download both of those in the correct datasets folder. And once it does, then we will have the two datasets we're going to end up using, or at least the base for it. Okay. So now that we've got them downloaded, we need to actually unzip them, right? So we need to actually take them out of this current state, which we'll do in just a moment. Now we're going to go ahead and unzip these files right here. Now I'm going to be using the command unzip. If you don't have this command, you can download it or you could just unzip these manually. So if you did it manually, that's completely fine, but I want to make it as automated as possible. So I'm going to go ahead and do it in the notebook itself. I'm actually going to change the name of this notebook because I made a copy. You don't have to be working off a copy. I just have it for historical reasons. But now we've got this download and unzip. And at the very bottom here, I want to actually create a few new folders here. Okay, so the first one is going to be the spam classifier directory. No big deal. And then the other two directories are going to be the outputs that we have from these curl commands and after they're unzipped. Now, of course, I always want to make sure that these are created. So I'm going to use those make dir commands that we did before. And now I'm going to go ahead and use unzip. So we call unzip, and then we can put in our input, which would be our output path from curl. So $that. And then our destination, so -d, is going to be one of these directories, right? So $that. Now, if you run this once, no big deal. It will unzip it. If you do it again, well, then it asks you this. Do you want to, replace the default? In other words, do you want to override it? So what you can do is you can put in the flag of -o. Now, the only reason I didn't put this in at the beginning is because curl -o means output, where unzip -o means override. So I'm going to go ahead and interrupt this because it was still loading. And now if I run it again, it should actually do it every single time. Okay, so I can copy this same thing for our YouTube one as well. The directory first, and then the path. And there we go. Okay, and so with that downloaded, we can actually take a look at the data set itself. So inside of my data sets, I now have this new folder here, right? And I've got a few things in here that we definitely want to look at. But if we see the YouTube one, notice it's only a few, well, these are musicians and it's comments related to these musicians. So it's not necessarily the best data set. Just off the bat, I'm pretty sure it's not the best data set. However, it's still spam and not spam related, which is why I'm going to keep with it. And this will become abundantly clear if during our training, we see some radical departures from the accuracy. So that's what we'll stick with, and I'll explain some more later. Now let's go ahead and take a look at these actual data sets. In this one, we're going to review and combine our data sets using Python pandas. Now, the first thing that I'm going to do is take one of these directories here, and I'm going to just look what's in there. So for path in one of those directories, .glob, and start out and just print out path, right? So this gives me the path to the files that are in there. And what I'm going to do is I'm going to hit try and print out path.read text. And then I'll hit accept and pass. I run that. And it only reads, well, it doesn't read the README text. It reads the spam SMS collection text right here. So that probably means that that's going to be the file I'm going to want to use, right? And so I'm going to go ahead and say that the SMS spam input path is equal to this / that. Okay. And so again, I can actually use that to read that text again, run it again. And what I see now, very first, is this /t. So this tells me that it's a TSV, tab separated values file. So I can use that inside of pandas. We'll talk about that in a second. But before I go any further with that, let's take a look at my YouTube directory, right? And so I'll go ahead and do for path in YouTube, glob, and then all, and again, printing out that path. Now when I print it out, I see CSV files, but a lot of them. It's not one single file like my other one. I had that README file, which probably has some good data in it, but I know that these are all CSV files, and I have a pretty good feeling that those are going to be useful for our data set. So we certainly need both of these. Okay. So speaking of our spam SMS collection, we'll do this one first because it's going to be by far the easiest one. And so I'm going to import pandas as PD, and then we're going to call this our SMS DF. DF for data frame. There's a very common distinction or variable for pandas data frames. And so we're going to do pd.read CSV, and I'll just pass in that path first. Oops, just the path. I don't need the whole thing there. Okay. And so I'll go ahead and do SMS df.head. And so, of course, I get an error because it actually is not a CSV file, which is what read CSV means. It's a tab separated value, which we can just do sep with that /t. And if I do that, now I actually have tabular data in here, right? Tabular data as in like a Excel file, right? So it's in columns and rows. That's what Pandas is really good for, is dealing with data that has columns and rows, not too dissimilar from an actual database like a SQL database or a NoSQL database. Okay, so we've got our read CSV in here now. But one of the things about it is this very first line. This, of course, is the column header, all of the columns. And in this case, it actually doesn't realize that there is none. So we have to declare it as header none, right? And there we go. So we now have a spam data frame that has head, and we can do tail, and we can actually say, the number that we want, like 200 values, and scroll through there. It's not going to necessarily show all of them, but we can actually see our data, right? And it's almost at a format that's ready to go for training. There's still a few things that we need, but what we see on this data is one side actually gives ham or spam. Spam is probably very obvious to you. Ham is just the opposite of spam, basically. Ham is the good value, spam is the bad value. So what we can do is we can actually treat these as the labels, and this over here is just like our text. This is what we'll be training on, both of those things. So we can say spam SMS, the data frame, columns, is equal to those values. So our label is going to be the first column, which will be this, right? And then our text. And there we go. So for all intents and purposes, this is ready to go. Now we need to do the YouTube one. This one is, well, not as straightforward, right? Because we have a bunch of CSV files in here. Now, one of the ways to only get CSV files is in this glob just by doing .csv. Now I only have the CSV files, which makes it a little bit easier. Of course, this is a pathlib distinction here, not anything to do with pandas. So within pandas, we can actually load up these data frames. So we can say df equals to pd.read CSV and pass in that path. And then it can print out df.head. Okay. And the way that Jupyter works is I should be able to actually use df later. So let me just comment this out and say df.head here. And so it actually does give me a data frame, but it's not the entire data frame, which we can actually tell by saying something like df and source. This will create a new column for us. We can actually pass in the string of the path, and we can actually see what the source would end up being. Or let's do path.name to make it a little easier to get the name of the file itself. So we see that it's only from Sci. That's what all of these are going to end up being because of how we loop through it. We are literally creating new data frames each time. Hopefully that's not that surprising. So what we can do then is we can actually say my dfs, as in a list of data frames that we can append this to. So my dfs.append that data frame. And then after all that is said and done, then I can say my YT data frame or my YouTube data frame is going to be pd.concat, which will just combine all of these. They will concatenate all of those. And then that way I can actually see that they're literally all in there. So the tail is still Sci, but the head should be, whatever the first file is in there. Cool. Showing us some good stuff. Now, one of the things it's also not doing, though, is we have this content, which I would imagine is the same as this text here. And then we also have a class of 0 or 1. So I want to change those two things. Okay. So first and foremost, I'm going to go ahead and say the df.rename. And we're going to change our column names. And it's going to be class, all caps. It has to be all caps. It has to match what's here. I'm going to change that to being our raw label, and then content. The content being our text. Okay. All of the other things I may or may not need, but for now I'm going to leave it like that. And then we need to declare in place being true. Okay, so now we've got a raw label and text. So in our case, the raw label is called raw label because it's either a 0 or a 1, right? And so we actually want to convert it to being spam or ham, right? Now, there is no technical reason to do this. In fact, later we will turn it back into 0 or 1. But since I'm prepping the actual data set, I will keep the original label. in this case, the original label I'm calling spam or ham. Now you can think of this in terms of the integer itself does declare what the label is, but if you had a bunch of different labels, then you would absolutely not want to keep them as a number. You'd want to map them to something with this data set prior to mapping them later, which we will map later for sure. So what I want to do now is say df and label. Again, remember how we created this column here. I'm now creating a new column. This new column is going to be based off of that raw label, but with a function applied to it. So .apply allows me to run a function. I'm going to use lambda here just to write it in line. Lambda of x is going to be the value of any given row in that column, so 0. So lambda x would be 0 in this case. So if I do the string of 0, right? Basically, I want to see if this string of 0 is, let's say, equal to the string of 1. Then I'm going to go ahead and say, well, it's spam. Otherwise, I'll say it's ham. Okay, so now we run that, run it again. And what we see now is those values corresponding correctly. So if it's a 0, we're going to say that it's ham. If it's a 1, we'll say it's spam. Now, I might actually have these labels wrong, in which case you could definitely go into the README file or even into the repository where we found this, right? There is no README file in this case, right? So I don't see one. This is just redundant data from whoever created this data set. But I'm just going to assume that this is correct, right? Is it spam or not? 0 being not, 1 being it is, right? Because it's not usually distinguished as if it's ham or not. It's usually distinguished if it's spam or not. And as you may know, 1 is often true or always true in the true false values of, something a bit like that. Cool. So now with that out of the way, we have two data sets. Both of them have text and label. They both have a source. Now, in this case, I'm actually going to change the source, right? So I can call this raw source if I wanted it for later, or I could say df and source being equal to, this is going to be my YouTube spam data set. And then up here in this one, I'm going to go ahead and also add a source, and this being equal to my SMS spam data set. Okay. So the only reason to have that is to distinguish it later. So like if at any time I need to look at my newly cleaned data set, I will have that. So I'm going to define df again, and this is going to be equal to pd.concat. Again, combining two data sets. The first one being our spam SMS data set, and then our YouTube spam data set, or data frame in this case. There we go. And then df.head, hit enter. And there is our new data set. Now, we have a bunch of columns we simply just do not need, right? So what I can do is I can declare the columns that I want. So what we can attempt here is inside of the concat, we can call columns equals to the label column and the text column. And in our case, the source column. Okay. So unfortunately, concat just won't do that, right? So that is a way that you can do when you are reading a CSV file. You can declare the columns from reading it, but you can't do it when you concatenate it. So instead of actually declaring the columns after we concatenate it, what I can do is declare it down here and use this instead. So the df, I'm going to go ahead and say raw data frame being in here, right? And so the raw data frame is going to rename everything. And in here, raw label, raw source, and just like that. Let's just make sure that's still working. It is. Okay, and then my df, it shouldn't be working, but it is. And so my data frame then is going to be a copy of that raw data frame. So raw.copy. And then inside of this copy, this is where we'll declare the fields that we want. So label and text and source. So basically I'm getting rid of all of the other fields in the iteration itself, not later, right? So if this ends up getting really, really big data, like really, really big, then it would be better to get the columns we want in here. In fact, probably earlier, but I actually had a few columns that I needed to use otherwise, like that raw label column I actually did end up using. So that's kind of the idea there. But now we have the full data set without that extra information that we just simply don't need for this data set. Now, I will say in general for big data, like if I was going to be storing this in a database, which I'm not going to be doing, but if I was storing this in a database, then I would keep all of the data. In fact, I probably wouldn't combine them here. I would store each one of them individually. The only things that I would combine are something like this, where it is the same kind of data, but then I would actually keep that, that actual path itself, the raw source itself. I would actually keep reference to that as well. But that's it. That's how we're going to go ahead and combine these data sets. The last part, of course, is exporting this. So to do this, we're going to go ahead and scroll very up to the top, and I'll go ahead and create export, and the directory is going to be our data sets, and export. And we'll go ahead and make that one. Make dir. Exist OK. And parents true. Okay, and then we'll go ahead and say dataset, or actually spam SMS, or spam dataset rather. Path is equal to that export dir, and spam dataset.csv. We're going to bring this down all the way. Let's make sure we run that cell actually. And now at the end of the file here, we'll go ahead and do pd.toCSV, or rather df.toCSV, this final data frame. And we'll use that export path, right? The actual spam dataset path. And we'll also pass index being false. We do not need the index value being the actual row value that it's in. Go ahead and run that. And that should actually give us our exported data set. Of course, not inside of spam classifier, but now inside of exports. And if we open this inside of VSCode, we should see all of this data, which should be a lot, right? It's not a crazy amount. It's only about 7,000, but it's definitely a lot more than it was, which I think is pretty cool. And so we have a way to just check these things out. And we now have the data set, so we just need to prepare this data set for training purposes. We only have gotten it to a point where it's ready to be turned into actual vectors for training, which we'll talk about in a moment. But that, I think, is pretty easy to do. Now, I will say there's a lot of things that we could have done here as well, which is like getting rid of duplicates. Like there's a pretty good chance that there's duplicate text throughout all of these, like repeated things said over and over. But I'm not going to worry about those right now. That would be something I would worry about in the long run. In fact, in the long run, I would hope to get a lot more data than this, like hundreds of thousands of lines, not just 7,000, right? So really, we just need something to start with. So that's what we're going to do very, very soon. So much of machine learning has its basis in linear algebra, which means that we do a lot of matrix multiplication and working with vectors. So what we need to do is we need to combine our data set and turn it into actual vectors. Now, you don't have to do the vector part yourself. We'll use something that Keras has, but we actually still need to convert our data set a little bit more in order for it to even be created into vectors. So what we're going to do is we're going to load in our data set. So let's load it in with pandas. So import pandas as PD, and just using everything that we've done before. And then we'll go ahead and say df equals to pd.read CSV of that data set. And then we'll do df.head. Okay. So the first thing I want to do is actually turn our labels and text into corresponding lists. In other words, label position, whatever position it is in, is going to match to the other position. So we'll go ahead and say labels equals to df and label, and then .to list. And we'll copy that and do the same thing for texts. Okay. And so the idea here is the labels at position, 120 is like actually corresponds to the texts at position 120 as well, right? So those should actually match up here. Okay. This is actually a good one because it shows us spam. Okay, great. So the idea now is once we have these items, we actually need to map our labels back into zeros and ones. Now, the reason I actually mapped them into ham and spam in the first place has to do with having multiple labels. And you would do a similar process with those as well. But I'm not going to worry about multiple labels right now. Instead, what I'm going to do is actually create my labels as int. Okay, so it's going to be based off of these labels here, like or let's say x for x in there. But I need to do something with x. And that is, of course, mapping it to something. So let's go ahead and create a legend. So I'll just say the legend, or rather the label legend, is equal to, well, ham being 0 and spam being 1. Now the reason for this is just to use it as a way to turn these into values that I can later unpack. I'll talk about the unpacking in a moment. So we see here, we need to run that label legend. Now labels as int is 0 and 1, right? And so again, we can use labels as int 120, and what we should get is, well, the label legend value, which would be 1. So this is actually what's going to end up being predicted for us. It's going to predict us a 0 or 1 value later, once we actually have it all set up. So we also need a label legend inverted, like as in the opposite value here. Now I could actually do this manually by actually writing it out. But again, if I had multiple labels, I wouldn't want to do it manually. I would actually want to do something more like the string value pair of, let's say, let me just do it. And then we did 4 KV, key value pairs, in those items here. And so this will actually give me the inverted values here. Okay, so now it's actually really important that we did change all of our labels to being ham or spam so we can have an actual proper label for it. So then when we do a prediction later, we can actually use that prediction to our advantage. But of course, I'm getting a key error string of 1. So what I want to do then is just turn this into this right here, key error of 1, because it's not a string value. Let's go ahead and do that. And there we go. Okay, so now it's giving me the proper values as we see fit. Okay, so of course this is what it's going to eventually be, so we don't need that yet. But now we have our labels are pretty much ready to be turned into categorical vectors, which we'll talk about when we get there. But for now, I want to just verify that these indices are correct, as in labels and text, right? I sort of did it here, but I definitely want to run a random sample for it. So I'm going to go ahead and import random. And we're going to grab a random number. So this is going to be a random like index number, if you will. And it's going to be random.randint. It's going to take in 0. And then essentially the length of labels or the data frame, whichever, it doesn't really matter. But the length of that. That way we get a random number that spans the entire data set, right? So we can run that over and over again. And all I want to do here is I want to assert that let's say the text of this random, index number is going to be equal to the data frame and going and grabbing the location of that index number and then .text, right? Just want to make sure that those are the same. So if I did +1 and they were incorrect, I would see something like this, right? That way we can run this over and over again. And of course, not just with text, but also the labels. And in this case, it's not going to be just the labels itself, right? So that's going to be a text label, it will give us the text label correctly. So we do want to try that one, of course, yeah. But what I meant was the labels as int, we want to make sure those are in the right direction as well. And we want to do it using the label inverted of the string of those labels, right? And just like that. Okay, cool. So again, just a really, really simple test to verify that we didn't mess up the indices, because they are so important, because these are the truth values of what this actually represents. Okay, so now that we have that, we're going to go ahead and tokenize our text. So to do this, we're going to import some things from Keras and TensorFlow. So from TensorFlow.keras.preprocessing.text, we're going to import tokenizer. Okay, so this might take a moment or so to actually import. Next, we want to have the max number of words that we're going to use here for our text. I'm going to use 280. And the reason is, oops, that should be pre-processing, not poor. There we go. 280 is the length of what a tweet would be, right? So it's certainly possible that the text that comes from YouTube is longer than 280. We want it to stop at 280, essentially. And so that's what we'll keep with. And now I'm going to go ahead and do our tokenizer. And we're going to have it just like this. Number of words being equal to that value here. And then we're going to go ahead and fit. We'll do fit on texts for our texts. Okay, that should take just a second. From there, we're going to go ahead and do our sequences and tokenizer dot texts to sequences of those texts. And we'll take a look at the sequences. Okay, so this is now better vectorized data. Okay, and we can actually see the number of unique tokens that are in here by doing our word index equals to the tokenizer dot word underscore index. And this will give us our unique tokens here. Okay, so each one of these word index actually gives us the value that corresponds up here, right? So 7, for example, is my. 9 is, and so on, right? So pretty cool. We have a way to actually tokenize all this data now, and it's done in a sequence. So it's not like it's just 0 and 1, but it's actually now ready to be, or closer to being ready to actually training this data. Okay, I think that's fairly straightforward. But the challenge of this is when we try to do matrix multiplication, we actually want our data to be, well, the same length all across the board, right? So this right here and this right here are not the same. As if we scroll up, we see that the first item has a bunch of text, the second one doesn't. Now, when we're doing matrix multiplication, we actually have to make sure that they are the same length. So the next part of this is actually padding the sequences, and this would actually finalize this for us. So we'll do from tensorflow.keras.preprocessing.sequence, import pad sequence. Okay. And so now this is actually going to give us our X data. So I want to give a max sequence length, and I'll give it at, sometimes you'll see it as 1,000, but it depends on how long we want this to be. This will remove some of the words that we don't want, right, or don't need. So if we look at this word index again, it's not going to have necessarily every single word or punctuation in there, but it could, right? It just really depends on how you end up doing that. So our max sequence length, I'll put at just 300. And so now we'll go ahead and do X equals to the pad sequences of all of our sequences, right? So the sequences we created up here. And then doing the max length to this max sequence length. Okay, and so there's our training data. Okay, it's completely ready to go as far as our training data is concerned, and it's all the exact same shape. So every single like actual vector in here has the same shape as every other one, unlike our actual data set itself. Okay, so now what we need to do is turn the actual labels themselves, the labels as int, we now need to turn those into a vector as well. And to do this, we're going to go ahead and do from tensorflow.keras.utils and import to categorical. And then we'll also import numpy. So import numpy as np. And then we'll go ahead and say y equals to, or let's do labels as int array. And we'll do np dot as array. and then labels as int. So this is just turning it into a NumPy array. And let's make sure NumPy is there. There we go. It's still the same data, right? It's still the same length and everything, but it's just what the two categorical expects. So now we have our Y two categorical of these labels as an array. And now we've got our Y values. Okay. And notice that it's actually now in positions, it does have 1 and 0, but now it's in what's called a one hot array, where position 0 is going to be related to, well, one of those values, right? So if we scroll up a bit, it's not related to this, but rather the position that they occur. So 1 is going to be ham, 0 is going to be spam, or position 0 is going to be ham, position 1 is going to be spam, right? So if it says 1 there, then it's on. We could obviously go through this a lot, but the idea being that each one of these arrays actually has all of the labels in it. And then if there's a 1 on, it actually signifies what that label is. It is not going corresponding directly to this label here. But we can actually see this, right? So if we look in the array itself, we've got 0, 0, 1. And if you think back to above, 0 was ham, 0 was ham, and then 1. Down here, being that it's a one hot, this is now saying that there's only 2 possible values for all of these. The very first possible value is going to correspond to ham, which is this 0 here. The very second value is not on, it's off, so it doesn't correspond to spam at all. So that's where these 3 things sort of line into, right? And so again, if we look at 0, 0, and 1 as being the ham, and spam, to turn that into a one hot array, we have 2 potential values for the label. So the 2 values are going to be ham or spam in that order, according to this. And then to turn this into a one hot array, it's going to be a new list here. So that first iteration is this right here. And so it's going to be equal to ham. So 1 and 0, right? So again, this is now correspond to that. And so the next value is again ham. And so 1, 0. And then the next value is 0, 1, because it's spam and it's this value right here. So the idea of one hot arrays is actually very, very common for the machine learning algorithms themselves. But to fully understand this, we would have to spend a bit more time on it. But hopefully the idea here that you understand is that we took our labels themselves, turned them into number representation of that label. From that number representation, it was turned into a vector with other kinds of representation according to it. So what we'll get back in our predictions are an array like this, where it actually has both numbers in there and a percentage for each one, like the percentage that it's a ham, like an actual ham score and a spam score. It's going to do it for both of them for every single time we run our predictions, which we will definitely come back to and we will definitely see. So that's pretty cool. So now they are fully into vectors, right? So what we need to do now is actually split up our training data and export it, which we'll do in the next one. Now we're going to go ahead and split up our training data and then export all of this stuff. So I really am working off of the previous notebook. I just duplicated it and ran everything. But before we do that, let's actually think about why we split up training data anyway. I want you to imagine for a moment you're playing a game with one of your friends. And that friend has a really, really good strategy to win, but that friend never, ever changes their strategy. They keep it the same every single time. So the first 10 games, they just absolutely destroy you. They do so well. They beat you in like record time every single time. But then you start noticing what that strategy is. You really start picking it up to the point where by the time you play your 20th game, they can never beat you because you know exactly what their strategy is and they never change it. Of course, games rarely work this way, but if they did, you would never lose to that friend anymore because you've learned all of their moves. You've learned every piece of data you possibly could about how they play. Now, in real life, you could potentially do this with a friend for a game that they actually do change their strategy. if you played enough games, you could probably eventually figure out all of the moves that they try and beat them every single time still, even if they do change that strategy. But that's rarely the case when you then face another person or 1,000 other people. So this is about varying our training data. We need to have variance in our training data. Otherwise, we're going to be really too focused on one way of being quote unquote right or being correct. And so we want to split up this training data as much as we can while we have time to, or at least in the early days of building out this algorithm. So that's the purpose for it. I do recommend that you do play around with this training data and split it up in different ways because you will yield different results. But as we grow our model or grow our data set, we will actually have new opportunities to split this training data more and also just add less and less variance to the potential outcomes of any given item, right? So in other words, if you could get every spoken piece of text that's ever happened along with labels of spam or not, well, then you might actually have the algorithm that will never get spam or not spam wrong. But of course, that's not going to happen yet. We don't have enough data for that. Maybe some like Google or Apple or Facebook, maybe they have that data, but even them, they're still working on trying to stamp out spam altogether. So let's go ahead and split up this data. It's really simple to do. We're going to be using the package called sklearn or scikit-learned called model selection. And we're going to import the train, test, and split. Now, this method itself is a very, very easy method to use. It looks like I didn't install it yet. So let's go ahead and install sklearn. So pip install scikit-learn. And so this method is incredibly common for splitting up data, but you can split up data however you like. This train test split is just an easy way a lot of data scientists end up using it. And it's based off of our X and Y values, right? So the X and Y value is convention. You don't have to call it this. You could have called this like features and this like outputs, right? But X and Y, again, is convention. So that's what we're going to stick with. And what's also convention is to take that X and Y and do X train, X test, Y train, and Y test. And yes, lowercase like that. I know it's probably a little weird for some of you, but then we run this train test split off of our X data and our Y data, and then our test size being some arbitrary percentage or between 1 and 0. And it's going to be 0.33 in my case, so 33%. And we want to randomize this. So the nice thing about this, what it will do is it will keep our indices for us, right? So that's the reason way up here when we did separate these things out into different lists and we were validating the random indice, that is why. We want to make sure that that is happening down in our training testing as well. And this package does it incredibly well. And that's really it. That's all we needed to do to actually split up this data. So now we're going to go ahead and export all of this data. And we're going to use Pickle for this. So import Pickle. Now the Pickle package itself can have malicious data. So in the case of our training here, you are not going to be using any of my X or Y data. Instead, when we actually go into training, we will recreate all of this stuff all over again in the actual training environment, which is not that big of a deal now that we've done it. Pickle itself is fine if you are the one manipulating this data. It's not great if I send you a pickle, like the actual output of this file, and then you run it. That's not a good idea. So if anyone does that to you, just don't take it. So we do need our training data though. And the question is, what is it that we need? Well, of course, we need these values that we just split up. And so I'm going to put it into a dictionary itself. So xtrain to xtrain and so on, right? And so, of course, the reason for this is, well, this is for sure values that we want. And, a lot of times you'll see this training split done in the same place as where you actually do the training itself. But I want to separate these notebooks out into guides themselves, which I do have, I've mentioned before. But the guides themselves are going to do a lot of these same things, but they're all separated out so you can really just focus on whatever that is. So this is the core of the training data. But the next thing that we also want to do is we also want to export our tokenizer. So we can actually use tokenizer.toJSON. So our tokenizer to JSON. This is a way to export our tokenizer data. So let's go ahead and also write this one, tokenizer JSON. Okay. And then we also probably want to have our max words in here. So max words. Now with the tokenizer, we might not necessarily need it, but I want to bring it in just in case. And the max words, of course, was up here, declared up here with one of these variables. There we go. And the next one would be our max sequence length. And again, scroll up a bit. Grab that one. Okay. And I also want to get my legend and the legend inverted. And that's probably it. So the legend, of course, I think we called it label legend actually. So we want those two things right here. Let's leave it as label legend and label legend inverted. And there we go. Okay, so I've got two pieces of data that I want to export. So the first one is we want our actual, where are we going to export this, right? So what is the path that we want to leave this in as? So I'm going to come up here and I'll call this my metadata export path. And we'll put it in as our exports directory. And I'll just call this spam metadata .pkl. Okay. And so we'll go ahead and do with open. And then we want to write bytes, pickle needs bytes as f, and then pickle.dump of that training data and to that file. Okay. Cool. And then we also want the same sort of string here for our tokenizer. And tokenizer export path, spam tokenizer, and .json. Okay, and bring that all the way back down. And this time I can just do write text of that JSON. Simple enough. And if we go back into our project, we should be able to see our exports in there. Looks like I have my tokenizer, but I did not run this one. So now I have both things. Okay, so my pickle and my JSON. Now in my case, this will not be in my repository. The spam dataset will be, but these two will not be. And of course, it's because you should not be running third-party pickle data. But that's actually all we need to do for splitting and exporting our data. I totally could have done this in an earlier step, but I wanted to give some time talking about splitting up the data and why it's important for our training. Now, I would also say another method that you could consider is taking this one step even further. So we've got our train test right here. We could actually do it one more or do it into 50%, right? So let's do 0.5. And then from there, we would do the actual test again. So let's go ahead and call this test, and I'll leave this in as T. I'm not gonna do this, but we will just keep it for a moment, T2. And so you would actually have X test and X valid. And so you would basically be taking out the testing data originally, right? So this should still be train, actually. So you would take out the original test data and split it up one more time so that you have another set of data that you could test, being the Y test and the validation. So this would be a way to do it 3 times, right? So to have 3 sets of data, which is also incredibly common. But again, I'm not going to do that right now. It is something maybe we do in the future. Our data set is really not big enough to have the validation set, another validation set or another test set in here. But as it stands right now, I think it's pretty solid. So let's go ahead and leave it here and get the training started. Now we're going to go ahead and train our classifier. So jump over to this blog post right here. This will have the most up-to-date information on the actual classifier training itself. But the main thing is actually just going down and clicking another link for launching this notebook on Google Colab, since it offers free GPUs, and then copy this to your drive, right? So the reason you want to copy it is so you can make changes, you can run it, you can do all of that stuff. Now, I actually already have one running, so I'm going to go ahead and scroll up to the top of the one I have running, because I'm currently using the free version of Google Colab, which means I can only run one session at a time, as in one training at a time especially. So the idea here is we are first going to install Boto 3 so we can have a place to upload this. I'll talk about the uploading in another portion, but for now, just make sure that it's installed. Next up, we are going to do the necessary imports that we've already seen with the addition of the actual model imports itself, which I'll talk about soon too. And then we see that we have our exports directory as well as a few other things that we want to use. Now, this prepare dataset is everything that we just did, which was getting the exported dataset and then actually running the portion of converting our exported dataset into actual vectors along with the pickle data and all of that. And so we can actually see the actual CSV file that comes out. This is the same one we just did. It's just all done now in this one actual notebook. But it's done because we, well, of course, already have that data set, but also we run a notebook itself. So up here, I grab this notebook and I output it to this part 2 guide here. This is that vector one, the creating or converting our data set into vectors. So it runs that notebook for me in line on Google Colab. Of course, that's important so I don't have to move this data around. I already have it on GitHub, so you don't have to move it around is really the key there. And so that runs, and notice that it's actually creating, random index. So it's actually checking that data again, and then it's giving me these tokens. And so from there, we can actually unpickle that data. This data is directly on Google Colab, which we can see inside of the files, clicking here, going up a little bit, and going into datasets. We see our exports here, and there's our pickle, right? This is not downloaded from GitHub. This is done in this training portion, okay? So after that training portion is done, we load that data back into a dictionary like we did when we exported it. We see what that data is. It has our inverted legend, our X test and train data, our Y test and train data, our tokenizer, the actual instance itself. It's not the JSON data. We'll get back to that one. Our max words, our max sequence. It has all of the data we might need. Okay, so make sure that whatever your max sequence is, it actually matches what you're training. In my case, it doesn't match what we talked about in the video. And so if we go down a little bit more, we actually can grab all of what that data was. And we can see here, here's that legend, right? That was our original legend. It's exactly the same. The inverted one would be the same as well. Next is our actual model. This is the actual training model. Now, I didn't actually create this model. This was done on Keras. Keras has a ton of documentation. There's a lot of really great machine learning data scientists out there that spend a lot of time trying to find the best model for any given problem area. This is one of the best models for the cross-category classification, which is this categorical cross-entropy. So this actually works for 2 labels or more, right? So in our case, we only had 2 labels, spam or ham, right? And so the key things about this for our data set is, of course, the max number of words, the input length. Remember how I said all of the training data has to be the same length? That's what that pad sequences thing did. This is important here. So you need to make sure that that's right. If you don't have it all the same length, then you're going to run into some serious issues. And so that's all that this is doing, is getting it, make sure that it is the same length. This gives me a number back. That's what shape does. It gives me the shape or the, like how wide and long a matrix might be. And then it adds some layers for us. LSTM is a type of model that is really common for text-related data. In this case, that's what we're doing, of course. And then our dense, this is our final layer right here. This layer right here has an output with 2 potential values. Those 2 values are going to be ham or spam. right? So if we had multiple labels, ham, spam, and not either, or let's say, for instance, if you were doing like news articles, it'd be like science, business, health, sports. It'd be 4 then, right? So that number corresponds to the number of actual Y, right? Y data, right? This thing right here, the number of keys in the legend. So that's important too. And then after we do that, we compile it and we make a summary. Again, you'll find a lot of examples of this, but the things I just covered are the important ones for definitely making it work. Now, the things that you can try out with are the dropout, the recurrent dropout, the spatial dropout. Now, there's a lot of detail and depth that we could go here. If you want to understand and know these things a little bit better, let me know in the comments. I think it is well worth learning about, but in the case of ours, we want something really practical, so actually going in the depth here would just take too long to getting this model into production. And it's already incredibly useful as is. It's kind of like, do you really need to know how to do an exponent, or do you really just need the value of that exponent? Yes, of course, it's probably a good idea to make the best possible model or even better models by learning and really understanding everything that's going on here. I totally agree. But the key to me is, does this spark your interest to learn more? If it does, let me know in the comments. Next, of course, we're going to actually go ahead and train it. So epochs is the number of times all of the data is trained thoroughly, basically. So if you want it to be trained very, very thoroughly, you can increase this number of epochs. Now, if you only do 1, it's probably not going to have the greatest training. But if you do 1,000, it's probably going to take way too long and probably not actually increase the value of the training. Like, it's not going to get any better. But the things that we see here is our fit data, right? So our X train and Y train, that actual split up data is here. Next, that validation data, right? So this is actually doing validation while it's training. So oftentimes it would be a good method to have another set of data that after all of this is done, then you can test on that. That's just not something I implemented at this time, but it's definitely something worth thinking about. And then of course, once this finishes training, which should be done soon, I did start it before the video, but it should be done soon. Once it's done, it will export this to Colab. It's not exporting it to Google Drive, just to Colab. So that means that once your Colab session ends, this will no longer work. We'll come back to that in a second. Then we're going to go ahead and predict some new data, right? So this is just arbitrary prediction, but this function itself is something we'll end up using in production for a lot of reasons. Now this tokenizer right here is based off of the tokenizer class that we had from that pickled data, something I did not do in a previous video, and it's not something I'll do in a future video either. But the idea here is we have the tokenizer working. Notice that we are converting the text string, whatever we pass as an argument, into a sequence. That sequence we then need to pad just like all of our other data, and then we'll run a prediction here. So these two are absolutely important to make sure that our text string is the right length of data for this sequence or for the prediction. Then what we get is an output like this. So it's going to give us an actual array value here where it's 2 values. It's 2 values because it's either ham or spam. And because we used softmax up here as our activation, this right here, we actually get a percentage back. So it's not going to be 1 or 0 like our labels have. Instead, it's going to give us, hey, this is probably about 93% this position. This is probably about 7% this position, which of course, this value actually maps to ham at 93% and spam at 7%, but that's only because, going back up to our labels, like ytrain, if we look at that, our ytrain label data, the very first position of any of these one hot arrays is ham. The second position represents spam, right? It's not about the number itself, which definitely can be confusing. But that's actually pretty cool. So that gives us this output here. Next, what's very common to do is get the top value, as in the top index value. In this case, for this example of 93%, the top index value, this would give me an indice that is 0. I can use that indice to get whatever the top prediction would end up being, which is not like necessarily going to be this right here. But the idea here is we actually have a prediction. In fact, this should be that right there. And so what we get then is our predictions coming back, and then we get our labels themselves, and that's what this will end up doing. So even if this part isn't working correctly, that's okay. It'll definitely work when we go into production and get it working there. The key thing here is really just to illustrate, generally speaking, what we need to do also when we turn this into an API itself, like into a FastAPI model that we'll end up using. So the final thing is actually exporting our tokenizer again and just the metadata we need to run inference. In other words, the metadata that will build up this prediction file here, as well as our actual model itself, right? So this actual model that's being loaded right here. So if we scroll down a bit, we see the tokenizer as JSON again, and there it is. So the final step after all of that is to upload it to object storage. This is what I'll do in a future part of the series, but for now, just know that uploading it into object storage is your best option. A big reason for this is because, well, these are cloud-based services that can store almost an unlimited amount of data because our model itself is going to get to be pretty big. So we don't necessarily want to download this locally, although I will on my machine. But if you start downloading hundreds of these, you'll start having, well, your entire system being essentially machine learning models. And they get really, really big, or they can. Ours right here is not going to be that big, so it should be pretty doable. So yeah, that's it. I mean, I'm going to let this finish actually training, and then we'll take a look at this prediction function. But the idea, hopefully, is fairly straightforward on what we need to do for the training. The model is almost done training, but the general idea is look at this accuracy already. The first epoch, it has 89% accuracy. Even the validation accuracy is actually pretty high also on that first training epoch. And then after the fourth one, it's at 96% across the board. And so perhaps that will be the best we can get right now, 96%, which I think is actually still really good. And then if we see these predictions, look at this. We run these predictions. There we go. We've got a input value here, which we can actually test out. Let me just bring this back to being our predictions here. And we'll put this at 0. And so we get this prediction value here, and it's giving us spam or ham for hello world and not spam. And if I say, something silly like buy my new phone for a huge discount, that seems kind of like spam to me. It gives me mostly spam, right? It's maybe not perfect, but if I did like and call discount and call some number, now it's a really, really much spam, right? So that's actually pretty cool. I think it's not perfect, but it definitely works. And we could get this into production and actually use it somewhere out there, right? The main thing here is actually exporting this or uploading this data somewhere. So that's actually what we'll need to do very soon, upload this model somewhere, because as it stands right now, there's really no way for me to upload this file. Because the key thing for us is we need to actually put it somewhere that I can then download it later. So I won't necessarily have to do this training again anytime soon, but I can actually use all of the results of this training, well, for a while. So let's go ahead and start doing that now. By all means, play around with this prediction function. I think it's actually pretty cool where it stands and how it's able to really just give us these values here. In a moment, we're going to upload our model and all the other model related data to object storage. But before I do, I'm going to just download it as well. So going into the file system here, you might need to go up a folder and finding the dataset folder itself into exports. The things that we need are the classifier metadata. So I'm going to go ahead and download that, the tokenizer JSON data, and then the model itself, the H5 file. Not the pickle file and not the CSV file. I certainly do not need the pickle file going forward. This actual training will do it again. Okay, so I just did that as a way to back this up because as soon as I leave this session, I'm going to have to retrain it again because this notebook itself is considered to be ephemeral, which means it's not going to keep any of these files in here permanently. Yes, I can attach Google Drive and I can totally do it there, but Google Drive you would not use in production on a web application. You could use it when you're testing things, but you would not use it in production on your web application. So instead, I'm going to go ahead and use object storage, and I'm going to be setting up two different actual object storage providers, which is Linode and DigitalOcean. By all means, you could just do one of these. They're roughly the same. I'm going to briefly talk about how to do it for each one, and then we'll actually just implement it on just simply one of them because they're roughly the same. And they're all using Boto 3, which is actually written by AWS for S3. The only reason I'm not doing S3 is because, well, it's a lot more cumbersome to set up S3 than it is these other two object storages. So inside of Linode, what we can do is we can create a bucket in here, and you can give it a label, whatever label you want. Give it a location that's probably close to you. And this one, I'm going to just call this inline CFE collab. I'm probably not going to keep that long term, and I'll go ahead and create that, right? So here's my bucket, right? Really, really simple. Going back into object storage, I'm going to go ahead and copy this whole URL here, and I'll go back into my notebook and scroll down to the Linode portion, and here is the endpoint I want to use, right? The region is right in here, US Southwest 1. The bucket name in the case of Linode is arbitrary as long as you have the endpoint, the entire endpoint like that. So you can call this whatever you'd like. Next, of course, are the access keys. We just go back into our buckets here. We've got access keys. We create one, CFE inline collab. And of course, in this case, it's probably a good idea to restrict your access to your single bucket because you're putting these access keys on collab. And if you accidentally expose them, like you can see my keys right now, of course, I'm going to delete them. But if you accidentally expose them, they would only be there for this one, hopefully this one single object or this one, training data right here. And so once I set that, I just run the cell and then I set it into my OS environment variables right here. And then I can run Boto 3 for all of those things. And it's really that simple. Now, if we go back into our actual bucket itself, we can see it going in here. There's our data set. There's our exports, spam SMS. There's all of our data, right? Simple. Going into DigitalOcean, it's not much different. Go into manage, into spaces, go to create and spaces. It's probably going to ask you for a project. Again, picking a data center near you. I'm probably closest to New York. You do not need a content delivery network in this case. We can restrict file listing. And again, CFE inline collab or whatever name you want to use. Notice the origin URL. You will need to put it into a project for DigitalOcean. We hit create space. This is going to create that object storage for us. And yet again, I'm going to go ahead and copy this, go back into my notebook here, paste it into the DigitalOcean stuff. I actually could put it right back into where Linode was. It doesn't really matter. The actual region is right there as well. The Linode one, I'm going to go ahead and comment out. That's not completely necessary because I could just run this cell. But then I need to actually go back into spaces and manage keys. And then we're going to get our space access keys, generate a new key, collab inline key, or whatever you want to call it. Okay, and so the first value up here is going to be the access key itself. And then the second value is going to be the secret key. And if you lose these keys or you need to reset them, by all means do that. Again, the bucket name in this case does not make a difference if you have this endpoint. And I'll explain again for both of them where that bucket name ends up going. The only place that the bucket name matters is on AWS S3. So again, I'll go ahead and run this cell here and then set the environment variables for those access keys, get those upload paths, and then just, perform the upload. Going back into DigitalOcean, into spaces, into that recently created bucket. There we go. Okay, so here it is, datasets, exports, and spam SMS. And there's all of our data. Okay, and it's not that big, right? 3.4 megabytes is definitely a workable model given where it's at. So this model itself can be retrained from this model, which we will definitely at least show you how to load this model back in. So the thing that I didn't mention or didn't show you really is the bucket name right here actually ends up turning into a folder for both places. So there's that folder. And on Linode, there's that folder right there. Again, in the case of AWS, that's the actual bucket name itself, not the path that you end up loading. So what we have here are the key names. This is the path as to where it ends up loading, which is why it worked the way it did. But this is how you would download it then, right? So you go ahead and download that, and that will download it locally in this method exactly. So that downloads it. I don't remember where I put it, but it downloads it somewhere in our project itself, which I think actually is probably in the content itself. There it is right there. And so it's in the root of the main content folder that the Colab itself works. Cool. And so now what we want to do is actually create a AI model download pipeline. But before I go anywhere, because just to be on the safe side, what we want to do is we want to get rid of those access keys, right? I don't want to accidentally leave them. So I'm going to go ahead and revoke the one from Linode, and then also go into DigitalOcean, manage keys, and revoke the Colab inline key as well. Okay, cool. So again, this is just when in doubt, do that as a way to ensure that your keys aren't exposed to anyone nefarious. That's one of the, I think, the biggest downsides of Google Colab is there's no way to securely just yet to add in environment variable keys. Maybe sometime in the future they will have that ability, but right now they do not. All right, so that's uploading our files. Now that we've got them, it's time to actually use a pipeline to download them. So we're actually getting a lot closer to actually using this model in a web application. If you pick nearly any file on GitHub, like in this case, I'm on a random models.py file, I can see that it's only 3 kilobytes, right? If I compare that with my trained machine learning model, it's 3 megabytes. It's nearly 1,000 times bigger. So that makes Git not perfectly suited for managing this file. And the other thing is, of course, machine learning model file exports can get a lot bigger than that. So object storage is a really good choice for these models. Now, of course, I don't have versioning in here. I don't have a history of these changes. That's something that I probably would want to have. But what I do have is a simple way to upload it, and that is something we've already seen using Photo 3. And it's really just this simple. It's these 3 lines right here. We authenticate using these access keys in our environment, and then we also use, just a few different configuration items here, and then we can upload a file. We can also use that same method for downloading that file. When it comes to the project we're working on, well, we need to download 3 files pretty much every single time we're going to deploy this code. So granted, we don't have to worry about deployment just yet, but we will at some point. And that's why I'm going to be using PyPyR specifically for automation pipelines. Now, if you've ever used something like GitHub Actions or CI tools, you have used YAML and some form of automation pipelines. So that's essentially what we're doing here. Now, I've also got a blog post on this one using PyPyR, and I'm working with the maintainers of PyPyR to make it a little bit better. But for now, I'm just going to go off of what I have here, and we will make a script, well, a pipeline and a script to actually download all of these files in a repeatable manner. So it's pretty simple to start. The first thing that I need to do is I need to make sure that PyPyR is installed. So in requirements.txt, there it is. The next thing I need to install is Boto 3. Save that. And we'll go ahead and do pip install -r and requirements.txt. Okay. So I have everything installed. The next thing, of course, is to create the environment variables. So .env. So .env files are very common for setting up our environment variables when we're working locally. You might also use these in production. You just won't move this file around. You definitely won't put it in Git ever, right? So in my case, it's definitely not there. It's done by default on the git ignore file, like ignored by default. And so the things that I need to put in here are really just this, right? So the AWS access key ID, AWS secret access key, and then these few other parameters. Now, these two are the primary ones we need in environment variables. We want to make sure that those values are hidden. It's another reason why in Colab, after I finished doing everything, I just deleted those keys right off the bat. And so it's actually very similar to like what we did in Colab, in which I will go ahead and reiterate right now. So let's go ahead and jump into any of your object storage. In this case, I'm just going to use Linode, but the exact same thing works for DigitalOcean in almost the same way. And the same thing works for AWS, of course, because that's what it was originally designed for. Anyways, so inside of object storage, I'm going to go ahead and grab my access keys here. I'm going to create a new one. This time, I'm going to go ahead and call this my local AI model download pipeline or something like that. Let's go ahead and say local AI as an API. Okay. And this time I could give it access to everything, but I like limiting the access to my keys in general. And I'll leave it with the inline CFE Colab bucket. We'll go ahead and hit submit. And then we're going to go ahead and copy these keys. And again, this is going to be local. Now, the nice thing about this is I can roll them at any time. Okay, so you might be tempted to put bucket name as, well, the bucket name, right? So inside of here, our buckets right here. You actually don't need to do that, right? So we don't need to put bucket name in here like this. Instead, what we can do is datasets. I'll explain that in a moment. Next, the endpoint URL is going to be this right here. And we're going to go ahead and use HTTP in there. There we go. The region name is usually in this endpoint URL. And there we go. I actually don't have to put environment variables in a string. We can just leave it like that. Cool. So now that we've got that, the next thing I want to make sure that's installed is python-.env. And sure enough, it is. Okay, great. So the main reason that we use this .env has to do with when we go into Python. So if I clear this out and I run Python and I do import os.environ.get, and we try to grab any of these environment variables, I'm going to see something like, well, nothing. So what we do then is we go from .env, that's that python.env package. We're going to import load.env, and then we're going to just simply load.env. This method is actually really powerful, and it will find where our .env file is. And so now I can actually get that access key like that. The other cool thing about load.env is if it doesn't find one, it's not going to raise an error. This is actually really useful because in some production environments, you might actually preload it with environment variables already, thus rendering this pretty much useless. So this is a key part here because the actual pipeline itself is going to be using Boto 3. So I'm going to go ahead and create that pipeline now. Create a folder here called pipelines. And I'm going to go ahead and make a new file in here. And this is going to be called AI model download.yaml. Okay. So there's a couple things that we need to declare first. First off is our context parser. And this is going to be from pypyr.parser.keyValuePairs. Okay. This is actually potentially a optional step, but it's nice to have a parser so we can add additional context to our pypyr call. Next, we're going to go ahead and do steps. And the first step, we'll give it a name of context setf. So pypyr.steps.context and setf. And what we want to do here is add context setf. We're going to give our context variables. Okay, so this is for our string substitution. Now, what is our local destination directory? Where do we want to store everything? I'm going to put it in models/spam-sms. And then what are my actual file keys? This, of course, are the keys inside of my object storage. So if I go in there, the key that we don't want to include here is this datasets right here. But what I do want to include is exports, spam SMS, and then one of these items, right? So that's what we'll do. And it's going to actually be all three of those items. So exports, spam, SMS. And I'll just copy and replace this 3 times. And then we'll go ahead and grab each one of these items. Okay, so all I'm doing here is letting this pipeline know that these are data items or context that I'm going to want to use in my next step. These are variables, so I set them specifically myself. You can set them however you like, because now what we want to do is the next step, which we're going to go ahead and do name. Now do keep in mind that I am tabbing things in. If you're not familiar with YAML, it's actually very similar to JSON. That is also very similar to a Python dictionary. It's just YAML uses spaces. Hey, a lot like Python. What do you know? And so here we're going to go ahead and just do pypyr.steps.py. So this step is actually going to allow me to execute Python. And we'll just go ahead and say n and py, use a pipe here. Now I'm going to go ahead and put in my Python. So in here, I can just go ahead and do that same thing I did in the shell, which was importing OS. And then we can print out os.environ.get. And that was the AWS secret key. And then we can go ahead and do from.env import load.env, and then load the .env, and we can print it again. Okay, very simple pipeline. Let's go ahead and give it a shot. I'm going to exit out of the terminal here, and I'm going to run pypyr. So python -m pypyr, and then pipelines, and the name of it without YAML. So AI-model-download. Hit enter, and there we go. We got an error. I think I put a capitalization where I didn't need to. Or rather, I did not put a capitalization where I should have, which is context set F, as it says right here. Let's try that again. And there we go. So it starts off with none, which was this, and then it gives us that key. Okay. So what this shows me is that I can actually now run all of the Boto3 related things. That's it. Okay. So first and foremost, let's just grab our other context here. So this local destination directory. That's another thing I could just add in there. And again, we can run that pipeline, and there it's showing us it. So now I'm going to go ahead and say dest path being pathlib.path of that destination directory. Now I'll go ahead and also import pathlib here. And I will pause for a second and say, yeah, it's probably a good idea to actually put this in its own module. But the reason I have it in the pipeline itself is so that in the future, if I ever need to change this pipeline only subtly for a lot of projects, I can. And then I have a new pipeline to handle that, which is, again, the reason I'm actually working with pypyr on making the best possible pipeline for this. So now that we've got this, I want to make sure that my destination path exists, essentially, right? So let's actually see what this path is. And I'm actually going to do .resolve. And I'm just going to print out that path. And again, we'll run it. And there it is. Okay. So the path is going based off of where I'm running pypyr, not where the actual file of this YAML file is. So that's pretty good. And what I want to do is I want to make that directory. So, well, destination path, make dir, and exist, okay, being true, and parents being true. Okay. So now I can not only get that path, but also do .exists and run it. And sure enough, it does. It does now. It didn't a moment ago, but it does now. Okay. And so this is another thing that I'm going to make sure I ignore. I do not want to check this in to GitHub. Now, the other part of not checking this into GitHub is maybe you don't want to open source your trained model. That's another thing to think about, right? You might want to open source all of your other code, but not your trained models. Those might be where all of your services value lies. Anyways, so let's go back in here. And so we now have the destination here. The next thing is, of course, using Boto3. We're going to import Boto3. After load.env, I'm going to start my session. And that's fairly straightforward. Straight, simple, and straightforward. That's going to be session equals to Boto3.session. That's going to start a session for us. No big deal. Next is going to be our bucket name. And this is os.environ.get bucket name. This, of course, is required. but it's still datasets. That is why I didn't actually put datasets anywhere. Now, in the case of Linode and DigitalOcean, this is our endpoint URL. Our bucket name does not have to be our actual bucket name for those services in this case. Okay, but I still need to use it inside of Boto3. Next up is our region and os.viron.get. And I think we call this region name. Again, we can hard code these things, but it makes a lot more sense to have this being reusable. Now, of course, the thing that I did hard code was the actual context that I'm using for this particular project. This part, this is why it'd probably be a good Python module itself. That's why I'm not actually doing it. It's just so we can reuse it and make it better later. Anyways, we've got our region, we've got our bucket. Now we're going to go ahead and create our client. Oh, we forgot one thing, and that is our endpoint URL. And of course, that's coming from here as well. So now we can go ahead and also say or none, because if you're using S3, you won't need to set your endpoint URL. It will do it for you. So I'm going to go ahead and do client equals to session.client S3, region name being that region, and our endpoint URL being that endpoint URL. Okay, so we've got our client now. And so now what I'm going to do is just say for key in file keys. Where's that coming from? These. It's a list, so I can iterate through them. That's context. So I'll go ahead and say the DL path is equal to the destination path slash, well, maybe the name of this key, which would be the root of that file. In other words, it would be this name instead of this whole thing, right? Because the destination path is just going to be in here. We don't need all of this. So the simple way to do this is just to say, let's say something like fname equals to pathlib.path of that key, and then just .name. This doesn't have to be a valid local path. It could just be a path-like string to get stuff like fname. There we go. Next, of course, is just simply client.download file, the bucket name we set up here in our environment variables. That's important. Next, of course, is the actual key itself. And then finally, the string of our local download path. And there we go. So that's our pipeline now. And so let's give it a shot. Inside of our models here, just going to press up and run it. It'll take a second, but there it goes. It downloads all of our stuff. Once it's done, it has everything. So the key thing for this is when I do go into production, this is what I'll have to run as a step in production. Now, I certainly can use PyPyR to actually manage all of those steps. PyPyR itself can call other pipelines in a step. Right? So it can call one of these, which is also really cool. But I just wanted a really simple way to always download this. Now, again, I know there's a lot of you that are like, well, why don't you just make this a Python module and just call it and just hard code these things in here? And I certainly could do that. But now in the future, for a future model, a different model, all I really need to change probably is the destination directory and these file keys, right? So the keys that I actually want to download. That's all I need to change. I don't need to change anything else. Right? Other than maybe my environment variable data, but even that I probably won't need to change, especially for this project. Furthermore, if I wanted to download more file keys, let's say, for instance, I have another classifier like a news classifier, right? I could do stuff like that. And that's, well, a really easy change. And perhaps I would change this to, news, whatever, news, like these keys don't really matter, but then it will actually download all of this stuff. Which is exactly what I wanted. So realistically, this is not an AI model downloader. It's just a simple way to download a file from Boto3. We are just calling it a AI model downloader as a good brand for the pipeline download. Now we're going to go ahead and start the API portion of this project. So inside of our root folder here. I'm going to create a new folder called app. Inside of there, we'll create an init file. So 2 underscores init.py. And then after that, we'll go ahead and create a main.py file right there. And this, of course, is going to be our FastAPI application. I'm going to close down the Explorer window for a moment and just declare the things we need to start off with. So from the FastAPI, import FastAPI, and we'll just declare app equaling to FastAPI. And if you've done this for any period of time, you'll declare a decorator called app.get, and this is going to define our read index method here. And this is just going to return hello and, world. Okay, simple enough. But what I want to do is I actually want to verify, at least here, that my model did download. So to get that, I'm going to go ahead and import pathlib. And let's declare a few things about this. First off, our base directory being equal to pathlib.path of this file. We want to resolve this, and then we want to get the parent. Okay, so we can verify this, of course, by, taking a look like this. Let's take a look. So uviacorn should be installed with FastAPI. So it's uviacorn app.main : app. So app, of course, is this folder right here. Main is the Python module. And this app is that final one. And then I'll just do -- reload and leave that running. Okay, so let's open this up in a browser, and there we go. So it gives us the root of our project, or at least seemingly the root of our project, but it's not quite the root of our project, right? So we actually want it to be the root of our entire project, so .parent again, and that gives me the root of our entire project, as in where models are. Now, this is the base directory I want to declare for, really just for FastAPI. Everything else in FastAPI should reference this base directory as the FastAPI base directory. The model directory, on the other hand, can use that parent. So the model directory is going to be outside of the FastAPI application. So we'll go ahead and do base dir.parent here, and then models. And so this is a good one where we can just check if it exists. Save it and refresh. Simple enough. Then, of course, would be all of the other files, right? So let's go ahead and start that off. So the model path and model dir, and we'll go ahead and do /spam SMS. Now, we're probably going to be using this again, so let's go ahead and do SMS, spam, model path, okay, or probably dir, and now model path. Okay, so spam SMS / spam model.h5. And we will repeat that with our tokenizer and our metadata. Okay, so those names are, I think, let's actually just verify what we called it by going into the model itself and just copying the path and pasting it in here. That was the metadata path. Put that there. And the tokenizer path. Put that there. Cool. So I probably don't need to check that all of these are available. And of course, if I zoom out a little bit, I can see that it's clearly on one line. Zoom in again. I just need to check that one of them is, and most important is probably the model itself. And there we go. Okay, simple enough. So the next part of this, of course, would be to verify that we can have some sort of input. So I'm going to add a query in here. And the query itself is, we want a default and an optional value, right? So the default, I'm just going to go ahead and say, hello world. And this time I'm going to get rid of everything else in here and just say query and query. Okay, so I refresh in here. There it is. No big deal. So now I want Q to be a value that I pass in. Q being a URL parameter. So something like Q equals to this is awesome, right? So now if I refresh in here, I have, well, no query, and I'm getting a validation error. So of course I want to make this optional. And to do that, we are going to import typing. So from typing, import optional. This gives a optional type to FastAPI, to this argument. So we can do optional string, and I'll just set that equal to num. So now it's just going to be Q or hello world. And so now if I refresh in here, there we go. And now I can actually pass in Q as well and say question mark Q, and this is awesome. And there we go. It's showing that, and it's responding back to what it was. All right, so we've laid the foundation pretty well to now implement our predict method here. All right, so we definitely need to write that out, and one that's, well, hopefully optimized for FastAPI. But the general idea is we have a method here. It does not have to be on the index route, right? It could be on a different path like /SMS model /predict. And it could also have a different HTTP method like post. But I'm going to leave it really simple, at least to start. And if we need to change it in the future, we will do that. But of course, now we just need to implement our prediction method. Now we're going to go ahead and load in our Keras model into FastAPI. Now, the way we do this is actually very similar to how we're going to load in, well, virtually anything we want FastAPI to depend on. Well, that is a database or this AI model. And we're going to do this in app.onEvent startup. So this decorator can be around any function. The function I'm going to call it is just simply on startup. And this is where I want to load my model. Okay. So the question then is, if I load my model, well, where do I load it to? So what I want to do is actually put a global variable here that I'll end up using, and I'm going to call this simply AI model and start it out being equal to none. And so in this AI model, I'm going to go ahead and load it in with TensorFlow. So from TensorFlow.keras.models, we're going to import load model. Okay. And so of course I already have a model path here, and that's what I'll use. On this startup event, I'll go ahead and say if model path.exists, my AI model is going to be equal to load model of this path. And I will actually declare the global AI model itself. This is only so that I can actually reset this, and it's for sure available elsewhere. Okay. So now I should have the AI model in there and running. So we can try this out by, well, let's just print out that AI model. And again, I'll use the global variable for it. And let's make sure our project's running. And I'm getting no module named TensorFlow. Okay. If I close this out and run pip freeze, I should have TensorFlow in here. And there it is. So to me, this happens from time to time with a virtual environment. I have to deactivate it and then reactivate it and then run uvacorn-m, or not -m, but rather just app.main:app and -- reload. And now I have no worries, right? Virtual environments just need to be refreshed every once in a while. But notice it does take a moment to actually load it in. But now we're all set up. We're all ready to go. It's really just that simple to load that model in. Okay, so it's definitely working. I can refresh in here and we're all good. But the other thing is I actually don't just want my AI model, right? I also want my AI tokenizer. Okay, so the actual instance of the tokenizer class. So to do that, we're going to go ahead and do from TensorFlow.keras.preprocessing .text import the tokenizer from JSON. Remember how we saved it as JSON when we uploaded it? There it is, both in the metadata as well as the tokenizer itself. So yet again, I'm going to go ahead and say if the tokenizer path exists, then the global AI tokenizer is going to be equal to the tokenizer from JSON. Now, this is from a JSON string, so I actually need to read that text. This is how I would open it using pathlib. So token, we'll just call it tJSON is that. And we'll use tJSON here. So again, I can go ahead and print this out, save it, and we should, well, Keras should be spelled correctly. And we take a look again. It loads, and we should get some sort of print. Oh yeah, POSIX path has nothing called exits. Weird. Should be exists, of course. Okay, cool. So now with the typos out of the way, we should have no problem. And there is the tokenizer class or object being printed out itself. So I feel pretty confident that that's there. Now, of course, the final thing is going to be our model metadata, and then probably our legend inverted, whatever that ends up being. So the model metadata, we have this as well. So if that exists, then we're going to go ahead and set it. And again, using the global variable for both of these. Okay, so the model metadata is going to be equal to the model metadata path dot read text. And I have to read that text, which is going to be unpacked JSON. So it's just going to be a JSON string. So I need to import JSON and do JSON.loads of that text. And now I should be able to print out that model metadata. In fact, not only should I be able to print it out, I should potentially be able to use it on my endpoint here. So let's actually do that. I'm going to bring in to my endpoint. I'm going to try and unpack that model metadata in there. This might be risky. Let's go ahead and see if it restarts. Looks like we're good there. Refreshing here, and there we go. There's our model metadata. It's a tiny file, so it shouldn't be that big of a deal. But there's our labels legend inverted. So I'm actually going to go ahead and rename this legend inverted to just label legend inverted and be the exact same name as the metadata may expect. Cool. So now that we've got this, I potentially could use some of this other metadata right off the bat, or I could actually set this one right here too. So I probably don't need to set this, right? I probably could just pass the model metadata around, but I might need that legend elsewhere. It's certainly possible that I will. Okay, so then if we use the legend itself, again, I'm going to go ahead and just say legend, and there we go. And just let it reboot again and see how it takes a moment to load in the actual mapping of everything. That includes the actual AI model. Imagine if you're doing that every time you try to do a prediction. Okay, cool. So now we have the foundation and we have loaded the model in and all of the metadata, the tokenizer. All we really need to do is make that predict function again. Now we're going to go ahead and implement this predict method here. So we're going to define it, predict, and it's going to take in the query, and then it's going to return a dictionary of some kind. So that's going to be roughly what we'll return down here as well. And so if you think about it, you might actually say, oh, well, the model itself, so the AI model, we can run predict on, right? So if we scroll up a little bit, that of course is the loaded model in from Keras. And I want to actually bring in the query here. Now that is maybe what's intuitive for you, but we have to remember back how we actually created this model and what we actually trained it on. Now this right here is of type string, right? it is not a vector. That is actually how we train the model in the first place. So we do need to convert this into its own vector, right? So we need to convert every single prediction into a vector. So thinking about this, we actually did it in this steps, right? Sequences, pad sequences, then we actually do the model prediction, and then we'll convert it into labels. So these first three are really how we did the training, right? It didn't do the prediction necessarily in this method, but that's essentially what we're trying to do here. We need to convert this query into sequences first, which is a vector, and then we will pad those sequences so they are the correct shape or correct size as our prediction needs. And then after we do that prediction, then we'll convert everything into labels. Okay, so the first thing is the sequences themselves. Now we already have the tokenizer. So to actually create the sequences, so sequences equals to that tokenizer dot texts to sequences. And this is the query, okay? But before we even jump to the query here, remember, this is a string. How did we train it? Well, we had texts, and it was a list of strings, right? And that's how we did our pad to sequences when we did the training. This is not any different. So we actually need to pass in the query as a list. So the other part about this is I could actually do predictions on many things. It doesn't have to be just one prediction, right? So that also means that my result is going to be, well, a list of preds, right? A list of predictions or an array of predictions. So that is something to keep in mind, okay? So now that we've got this, we need to pad those sequences, and that will be our input. So that's going to be pad sequences. And that's this right here with a max length. And I'll put that in as 280. Okay, so let's make sure that this is imported. And that is from our preprocessing.sequence, import pad sequences. Okay, so we now have our input. I'm going to go ahead and do our prediction. And then this is going to be our preds list. Okay. This should only have one value in it. Like it has a list, or well, better to call it an array because that's what it is in terms of NumPy. I'll explain that in a moment. But this is going to be an array with one single array in it. Think of it as well in terms of Python. It's a list with one list in it. Okay, we'll take a look at that in a moment. But before we go any further, this max length here is going to catch you up a little bit, especially if you've been following exactly what I've been doing. In other words, if you look back to our local training, when we actually converted our data set into vectors, we have this max sequence length of 300. If you look at our model training, the actual training, we have a max sequence of 280. So the reason it's 280 here is only because the version of converting data set into vectors in production, the actual GitHub repository has it at 280. When we did it locally, we had it at 300. So to save confusion, you can absolutely change this to 280, and that way all of it is consistent. But I wanted to bring it out to make sure that you knew that we definitely want to use the same length of the sequence all across the board. If you use too small of a length or too large of one, that means that our input may or may not be actually accurate. And thus our prediction may or may not be accurate as well. Okay, so just keep that in mind. So I am going to use the one from my exported model metadata based off of the fact that this production run part was going off of the one on GitHub, not the one I did locally, right? So it's definitely a different notebook, which you would see if you looked at it. Okay, cool. So now with that, I'm going to go ahead and grab that data. And that's going to be our sequence length. So I'll just call this max len equals to model metadata. And the value we put in there was just simply max sequence. So I'll do get that. And I'll also say or 280. And then I'll just pass in 280 here. Okay, so this is going to be our prediction. That's our predictions array. So I can go ahead and print that out. And I can also print out the X input. And let's also print out the X input.shape. Okay, so we'll save that. Now we'll go ahead and run this prediction. I'm going to get rid of this print statement down here. Okay, let's make sure our server is still running. Sure enough, it is. No import errors or anything like that. So let's go ahead and look at our run. Okay, so there it did. It did a quick run. Here's the X input. Notice that it has brackets on the outside and on the inside. So this is an array of one single arrays. It's very similar to a list, but as you noticed, there's no commas, right? So that's why it's not considered a list. It's considered a NumPy array. NumPy arrays will give us a shape. So this is a one-dimensional array, which is very similar to a list, right? A list is a one-dimensional array, and it has 280 columns, basically. Okay, cool. So the response is this right here, also a list of one single array, right? So it's basically saying this input right here ends up outputting this value right here. Okay, so in other words, our actual prediction for this input is the preds array, the first element in that. So we refresh in here, and what will be printed out once it's ready is, well, it should be the first item. Oh, I didn't print it out. Let's go ahead and print it out. Okay. And so it's only going to be this element right here. Okay. So this is important just to understand that you can absolutely very easily get that organization wrong, right? So in other words, I could do all sorts of things with these predictions, and I could also put in the wrong query itself. So it's not necessarily that straightforward, because the answer that would come back from it isn't necessarily wrong either, right? So here we go. There's our predictions. Okay, so let's actually take a look at what I mean by this. Now, let's get rid of the query out of the list. Okay, save that, and I'll let it reboot a second, and then we'll refresh this again. I run it. This time, quite a different shape, but I get results still. Interesting. Now, if I actually looked at the entire results themselves, right, so all of the predictions, not just the single one, I can see that it's actually giving me too many results. Okay, so let's go ahead and refresh that. And there we go. There's these too many results. Okay, so as we notice here, this too many results is because it's essentially taking this query and it's treating it as if this is a list of text sequences. It's not, but that's what it's trying to do, right? It's kind of giving us back the data we're sending in. So that subtle change, has a huge impact on the actual prediction. Next, of course, is the length itself. If I did 100 here, so definitely lower than what I initially trained it on, and ran this again, might take a moment for that to boot. I get a warning. It's got the wrong shape, and I get some weird prediction back as well. It might actually be accurate or very close to accurate based off of what I'm inputting, but look at this. It's all zeros. The actual input itself is, well, practically like saying nothing. And practically like saying nothing will tend to lean towards not being spam. Okay, so yet another reason to make sure that we've got that sequence down. But what's cool though is once we do have it correct, we now have a proper predictions array with roughly a percentage. Okay, so if I actually change this into a list, we can now see what our preds are. This is now a Python list, and we take a look at this. Looks like I didn't print out the correct one. Let's save this again and refresh in here. Now what we should see is the values as a list. Pretty cool. And so what I want to do then is I want to turn those values into a dictionary of some kind. And so what I'm going to do then is I'm going to now say our labeled predictions, well, are going to be equal to, let's put it in as just a dictionary first. And so the label itself, what's the label? And then what is the confidence score? Okay, so if we did each individual one of these, so the first one, right, the first one, well, that's going to be iteration 0, and the label itself would then also be iteration 0. or the confidence score itself. Print this out. Now remember the label, well, we actually had a labels legend inverted. So that label is going to take the string of that value, that iteration, and we can get that string value just like that. And the confidence will be this score right here. And if I turn this into a float, then it's going to be a floating point number in Python versus a NumPy number. Okay, so we save that and we refresh in here and we'll take a look at the value we get. And so we got label ham, confidence. That's the score we got. Cool. So that is now showing me that we can actually convert our original prediction into, well, a list of predictions. Okay, so this is just a simple way to do it. Now, to actually turn it into a list comprehension like that, we put a bracket around here, and then we do for, let's say, I and X in preds. Well, we have to enumerate those predictions. And so the I itself is the iteration number, which is what we were emulating here. And then the preds here, we can also use the iteration number, or since I'm actually iterating through those predictions, I can just use the value of X there. And so when we save that, what our label predictions will be is the values or the percentages for each label. Pretty cool. Okay, so not quite done though. That's going to be our overall predictions. What about our top prediction? How do we actually get our top prediction? So there is a value in NumPy. So let's go ahead and do import NumPy as NP. Move this up here. And so in NumPy, what we can do is we can get the top value in our predictions array here, right? Or this list here. So I'm actually going to remove this from being a list again, turn it into a list down here when we need it to be a list. And now what I want to do is get what is the top index value here. So top IDX and val, and that's going to be mp numpy.arg max of these predictions. So this will give me whatever that top index value is, which means from that top index value, I can then give these responses right here, the same thing, right? So then we can say top, pred, and set that equal to a dictionary, use these values here. And so, or the dictionary should be from the label itself. Okay, so the label inverted. This now is going to be that index value. And again, we can actually use our preds here and the index value that we have. And then we can turn this into a float. Now, we don't have to turn it into a float, but turning it into a float means that when we actually load this through JSON, it'll come out correctly. Okay, so I'm going to keep on with this and say the top is going to be equal to this top pred. Oops, that should be, there we go. So that's our top prediction. And then all predictions is going to be this labeled prediction list. Okay, so now we have a full-on prediction function with the top prediction as well. Now, of course, we don't actually have to have that top prediction. The only reason I have it here is if I ever change this to having many different labels, this function would still work. So it only really needs the predictions response, but we'll keep it in with top. And so now I could say preds, dictionary is equal to that predict. And now we'll go ahead and unpack that whole thing. Okay, so we've got our query, and actually maybe we want to make this a little bit more like results and our dictionary that's coming back. So we're going to go ahead and save that, refresh in here. Now it should do our prediction, and we've got our top value here and all of our values, right? And so let's go ahead and remove the float from these elements here and see what happens. So instead of having a float on these, no floating point number, we save that. We refresh in here, we'll get an error, right? Internal server error. And what we see is this NumPy float32 object is not iterable. Okay, so what's actually happening here is the prediction is giving us back NumPy numbers. It's not giving us back floats. And what FastAPI is trying to do is dump this into JSON. Okay, so let's go ahead and leave those. Actually, I'll leave them as floats for a moment. And we'll import JSON. Oh, looks like I already have it imported. And so I'll go ahead and do JSON.dumps of that value and try that same thing. Refresh in here. And I should get the exact same error or something very similar to it. And so now it says the object type of float32 is not JSON seriable. Okay, so that is why we actually can convert these into the own floating point numbers, right, in Python. Now, another way to actually just do this is, well, we could implement a NumPy encoder. This is something that's seen fairly often when it comes to working with NumPy data, is we would have this NumPy encoder then and do JSON.dumps of that data with the class of the NumPy encoder. And then we just do JSON.loads of that data, right? So essentially it encodes it into the correct JSON, and then we load it back into a dictionary, a Python dictionary. So then the actual final response would be something like this, okay? And so now I didn't actually convert anything manually into a float. It just does it for me. And so I can actually reuse that over and over again, right? That actual encoder, and I can use it for all sorts of things, which is why I think this is pretty cool. And it's fairly straightforward as to how it works. I do already have NumPy installed, but now we actually have a way to run this as usual. And it's going to use the standard JSON encoder anyway, so it's not like it's changing much. It's just checking if anything inside of that JSON data is a NumPy type that we need to convert into a JSON ready type, right? So just a standard Python type. So that's how we can actually perform those predictions. There's a lot to this, and it's actually not that great in the sense that it's not formatted that great, right? So I have this loading, I have all this stuff for loading, I have all this stuff for actually predicting. What I want to do is change this into being a proper class. But at this point, we could totally go off of this and we can absolutely change the model itself. As long as it's a text model, this will actually run a prediction on it correctly. But of course, if it's an image model, it wouldn't work, right? And then this encoding portion, that would be another step that we'd probably want to have, as well as getting the prediction labels and all that. So let's actually clean this up by turning it into its own class, so it's just slightly different than what we've got here. In a moment, I'm going to be refactoring my project a little bit. And this process is a bit tedious because we're really just re-implementing a bunch of things that we already did. Now, in my philosophy, I think that the sooner you get something done and released to the public, the better. So actually doing this refactoring or watching how it's done is not necessary. You could just go in and grab the code itself. So ml.py, encoders.py, and then updating main to do that. So this is the result, this right here and this right here, instead of the long thing that we had before. So main.py ends up being a lot more focused on simply FastAPI itself, not all of the other things it could potentially be focused on. Now, we could also refactor this a lot more as well and just make it a better data class or a better model class itself. But again, I don't want to spend too much time on the tediousness of making this particular thing better, because really what this is all about is deploying an AI model into production so we can get more data. This is still going to be a microservice. There's not going to be a whole lot beyond doing the predictions and storing that data in production. So I will say, if you want to skip this part, by all means do it. It's a little bit long. If you don't want to skip it, let's go ahead and jump in right now. All right, so where we stand right now is our FastAPI application is really just our machine learning model. So we want to change this to being its own class, and it will actually help us clean up our FastAPI stuff, but also make our machine learning stuff a little bit more reusable. So let's go ahead and jump into the app itself, and we'll go ahead and create ml.py. So the first thing I'm going to do is import from data classes. We're going to import the data class decorator here. And so if you're using an older version of Python, like Python 3.6, you will have to do pip install and data classes. Okay. So what we want to do here is I'm going to define a data class. So let's say class and AI model. And this is going to have, first off, our model path, our tokenizer path, and our metadata path. Okay. So each one of these things is going to be paths that we'll use and initialize. So that means we're going to define a post init method here. And based off of those data, actually we don't need to run anything, but based off of what's here, we will then define our model, which will set to none, our tokenizer, which will also set to none, and then our metadata, and also to none. Okay, so to do this, it's pretty simple. So we say data class, and now when we are going to go to initialize this, it's going to have those three paths in here, right? So it's going to be something like this, where it's equal to that path, right? Equal to path, and so on. And so doing this then means that this class, whatever that instance ends up being, will be primarily responsible for doing everything else, which would include our predict method here, right? And it would take in our query, and then it would return our examples, okay? So the first thing is, let's actually declare the model path itself. So we're going to go ahead and do from pathlib, we're going to import the class of path, and we'll just set this equal to path, or of type path, that is. And the tokenizer path and metadata path, well, we could actually think about this in the long run as being optional. The reason it's optional is because, well, what if I use this AI model class for a image class, right? Or something like that. So that way, I'm going to go ahead and do from typing import optional, and come down in here and say optional path, set that equal to none as well, and do the same thing for our metadata. Okay, so now in our post init here, I'll just go ahead and say if self.model path, well, it should have self.model path, right? So I really just want to do if it exists, then we're going to do self.model equals to, well, we need to load model of that self.model path, right? And of course that load model import is this right here, which we did on main. Okay, simple enough. So now in this predict method, we're going to have to go ahead and do get model and return self.model. And of course, if it's not in there, we'll go ahead and say if not self.model, then we'll go ahead and raise an exception. Model not implemented. Okay. So we could also have our own exceptions, right? So if I came in here and did class not implemented, we could give it a class of exception and do all sorts of cool stuff with that. Now, I'm not going to spend the time to do that right now, but that would be a way to start making your own exceptions. Okay, so now we've got our get model here. So model equals to self.getModel, and then model.predict. Uh-oh, we got our query here. So what do we need to do with the query? Well, this is actually going to change to being from predict to predict text. And, well, we need to convert our text into a number of things. So what I need is my X input from this query. So get input from text, and that's going to be query. Okay, so I'll just do self dot, and then we use this method here, and again, self and query. And so now we need our tokenizer, right? So in this case, we'll go ahead and say if self.tokenizerPath, then if.self.tokenizerPath.exists. So if the actual value is implemented on the model, and then if it exists, then we'll go ahead and say self.tokenizer equals to, well, let's think about how we did our tokenizer before. First off, we did load from JSON, right? So we need to bring that in. So I'm assuming this tokenizer will always be JSON. We could add in another path or another condition in here and basically saying that it is JSON. I'm just going to assume that it is, which is probably not a great idea, but we'll do that. So self tokenizer from JSON. So the tokenizer text equals to, self.read text. And so there is our tokenizer. Okay. In fact, let's go ahead and say if not self.tokenizer path .name .ends with JSON. Then I'll just go ahead and, or let's just say if it does, then we'll go ahead and have our tokenizer load in. Okay. I could raise an exception in here, but I'll just leave it like that. Okay. So this is checking the path name that it ends with JSON. This will load it in. Great. So now we've got our tokenizer. So tokenizer equals to the self dot, well, yet again, I actually want to do an exception if it's not there. So this time being self.get tokenizer. And now the tokenizer is not implemented. So there we go. And we already did the hard part of this, which was the X input. So we've got our tokenizer stuff right here. So it's sequences, right? So really this is our sequence. So now we'll go ahead and say define get sequences from query, or from text. We can leave it in as from text. And we'll go ahead and put the query there. And now we'll go ahead and put this up here. Okay. So it actually kind of makes sense to me to, instead of having our X input being from these sequences, this would be get input from, instead of text being from sequences. So now get sequences from text. Our tokenizer is this. We return that sequence. So now our sequences equal to self.get sequences from text and query, right? Or we could call it text to sequences, but I like getting sequences from text because it's, well, not conflicting with the Keras name. Okay, simple enough. Now we've got our sequences here. Now, another thing we can consider here is having this as a list. So our texts being a list type. And so I'm going to leave that in as texts here. And we'll place that there. And we will give it a type. And this is from typing. We'll import list. And so list of strings. Okay. So then that just means down here, just like we've seen before, I'll put that query in like that. Okay, so we're just going to assume this query is a string. This just gives me some additional flexibility if I ever do want to have a list of texts instead of just one single one. Okay, so now we've got our sequences. So get input from sequences. We'll just rename that one. Okay, and then going back into main, here is our sequence related stuff, the actual X input, right? So again, our model metadata, it's going to be, well, just like our tokenizer, just like our model. So we're going to go ahead and have this here. So metadata. So get our metadata, 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 metadata. To implement it, very similar to this. Okay. And so back into main, how did we load that before? Well, here it is right here. Am I going to leave out the inverted stuff? So ends with, I definitely want to use that same ends with JSON. Okay, so now it's simply self.metadata is reading that text and then doing JSON.loads. Okay, so we need to import JSON. There we go. So now we've got our metadata, hopefully. So scrolling back down here, so it's now self.get metadata, got our max sequences. Our sequences should be the actual input here. We've got pad sequences. Did I import that? Nope. So let's go ahead and import that one. Okay, and so now we've got get sequences from text. There we go. Our X input. Cool. So now we can actually run that prediction, right? So this, of course, is going to be our raw preds. And then we'll return that. Or should we actually format this? And I would say yes. We'll go ahead and do include top being true. Okay, so let's actually talk about the formatting of it. Let's go back into our main.py. So we've got our formatting right here. So our top So we've got our formatting, well, right here. So we've got our formatting roughly right here, right? So the label and the confidence, okay? So the first thing is label a pred, okay? So I'm gonna label one single prediction. And so that one single prediction is gonna have to get the label's legend, right? So define get label legend, takes in self, and again, we'll get the metadata itself. So legend equals to self.get metadata. And this is going to be our legend inverted, actually. Okay, so .get and the label legend inverted. All right. So if the metadata is not there, then we've got that. And I'll go ahead and say, or just an empty list here, or an empty dictionary rather. And so now that we've got that, we want to return that data. Okay, so the actual data that's coming through in here is going to be our index or our IDX value, right? So that's what we see right now. So the IDX value would be from the label legend. So now I don't need to have all of this, but rather just the legend itself, and then the string of that IDX that gives us our label. Okay, and then the prediction, well, I don't necessarily have to have this in as that, but rather just the value itself. And so I'll come in with that value. I'm not going to change it at all. We'll just leave it as the raw value. Okay. And so this will give me, well, I actually did the whole label prediction here. So let's go ahead and cut this part to being down here and just return the legend this way. So legend equals to self.getLegend, and we'll pass the IDX in our label. So get the labeled prediction. Okay, and so this would give me the opportunity to raise an exception if there isn't a legend in there at all. Okay, because, well, there probably would have some issues here. So I'll just say if the length of legend.keys is not equal to 2, then we'll raise an exception. Your legend is incorrect. Okay, so this actually should be based off of a whole other thing that we should have had in our metadata, like the actual potential for those labels. But I'm going to leave it like this just to simplify what we currently have. We can make this improvement much later. So anyway, so now we have our legend here and we can get the prediction itself. And so now from these predictions, well, I want to actually update what this value would end up being. So the labeled preds is equal to, well, we've already seen this. Go back into main, we've got our labeled preds right here. And we can paste that in. And so this time, instead of actually doing each individual one, we'll just get the label prediction. And we'll do self.getLabelPred, the index value, so that's going to be I, and then the actual value is X. And that's how we actually go through and enumerate that. Okay, so now what I'm going to do is I'll say results equals to the predictions and include those label preds, and we'll return that results. Okay, so now what I want is the top one. So this. So in here, we'll say if include top, Then I'll go ahead and say the results.top equals to self.get top pred labeled of the predictions. So preds. So that means up here, we're going to go ahead and do define get top pred labeled. And it's going to be self and preds. Okay, tab that over. And then we'll return that. So yet again, I need to do basically this. So let's get rid of this. And top preds, well, the index value is this. The actual value of it will just be simply the value is preds of whatever that is. There we go. And we can just return that. And now we've got the ability to get top pred labeled, the results, everything like that. There we go. So now we have an actual class to do our labeling and our modeling and our prediction. Cool. So now back into the FastAPI app, let's go ahead and get rid of a bunch of things. One of the things that I did leave out was the encoding, so we'll bring that back in a moment. So let's go ahead and on startup. Now it's going to just be global, maybe like our AI model instance, or let's just say AI model. Okay, and so we want to import it. We'll leave it in as AI model. I'll do from dot import ML. Okay, so global AI model is going to be AI model equals to ML dot our model class name, which is also AI model. And of course, I need to pass in all of these paths here that I want and set them to their proper values, which were set up here. So model path and model path, tokenizer path, tokenizer path, and our metadata path. Okay, so now we've got our AI model. I no longer need these. I just need this. And so this now will be how we run our prediction. AI model.predict and text. No longer need these. Cool. And so, of course, the next thing is going to be getting rid of all of the TensorFlow related imports. And then our encoder, I'm going to go ahead and bring that in as well. So I'm going to make a new file called encoder, or encoders rather. Just going to be that exactly. Import JSON. Okay, so then back into main, we'll go ahead, or rather back into ML, I'll go ahead and import this. So from dot import encoders. So now in our prediction function, we'll go ahead and say encode to JSON being true. Okay. So that means then we'll use our encoder. So encoders dot, well, actually we have our NumPy encoder here. So I'm just going to call a new class and call it encode to JSON. And it's going to be whatever data. And it's going to return JSON dumps that data class equaling to the NumPy encoder. And we can actually do it where it's saying encoded equaling to that. And then say as high. So if as high, then we'll return the JSON.loads of that encoded. Otherwise, we'll just return encoded. Okay, so back into ML. Now, encoders.encode to JSON of the results, and we'll declare as pi being true. Okay, so encoded data or encoded results, and then just return that. Cool. So we definitely could have this being false, of course. So I'll just change this to being simply results. So if encode to JSON, just like that, and then we'll just return our results. Great. So now back into main, we can get rid of maybe any other imports that we might have not used anymore, like our NumPy import. Don't think we use that. JSON, we might use it again. I don't think we need it right now. But now it's a little bit cleaner. Okay, and so let's go ahead and make sure everything's running and we have no errors here. Getting a syntax error. I need a comma here and here. Okay, and so we, not in a slow way whatsoever, took a while to get here. Okay, so we've got a legend error. Okay, so we're getting our legend is incorrect. So let's go ahead and print out our legend keys as well as our metadata. Okay, and I refresh that. Empty. So that must mean that we are not getting the correct data out. Must have not saved it correctly, so let's go ahead and do it again. And legend is incorrect. Scroll up a bit. And there we go. So inverted does have 2 keys. Let's make sure I labels inverted. There we go. Use the wrong value, key value in that label legend. Okay, so now I should actually have a lot of things okay. NumPy is not in ML. Import NumPy as NP. Okay, here we go. And we refresh. And there we go. So everything's being printed out. And we're now getting those predictions all labeled up and ready to go. I do have a problem. It's only labeling, well, one thing. So let's go ahead and take a look as to why. In our prediction function, it's probably related to the preds that are coming back. Remember, the input is multiple things. So we actually want to get just one iteration here. So we put that at 0. That should solve that problem. Okay. We've already seen this. So if that's confusing at all, let me know. But now we've got it. Okay. So now, that was not a short way to get to a point where our FastAPI app is a lot more cleaned up. In fact, you could argue that we probably should have done this class first. And I tend to agree, but there's a lot of tedious things that go into this that don't really give us the results that we want as fast as we want. And also, you probably could have just skipped this step altogether and really just copied and pasted it, or just use whatever you'd like, right? The other one still worked and it was still valid, and we could have just copied and pasted the other one as just importing this single function. But I wanted to make this maybe a little bit more reusable for the future as to how I might end up using this actual data in this actual class if I changed to, whether it's to a new model and all that. So going back into main.py, what I actually want here is my spam SMS model, or really my spam model, because that's really what we're seeing here. And so now it's a slight change, but this actually makes a lot of sense to now have an endpoint for spam, right? Now, I'm actually going to leave it in as AI model, because if I am actually going to be using multiple models, I would have to change a number of things, not necessarily just this. In other words, I don't want one single application to be actually serving a bunch of different models. I would want my one application to serve one model. In other words, this REST API application should really only be serving this one single model, maybe two, maybe three at the most, because each model itself takes up a good amount of memory. So it'd be better to just duplicate this all over again for a different model. But of course, the actual model class itself would also maybe need a little bit of changes to make it completely reusable. This REST API has three primary purposes. Number one is to provide really good predictions on whether or not a string of text is spam or not, right? And then number two is to improve the conditions to which it can make better predictions. And then number three is to actually have this open and in production for other applications or users around the world, right? So what we're going to be focusing on now is number two, is to improve the conditions that we can make our model better. And a big part of that is just storing the data here, right? Storing what's being predicted on, and then storing maybe some of the results or all of the results. And to do that, I'm going to be using a NoSQL database, which you probably already know, called Cassandra. And this NoSQL database is going to be managed by DataStax, and specifically with the AstraDB service. Okay. So they definitely did sponsor this, but the idea here is we want to sign up because you get 80 gigabytes of free data monthly. That's a lot, especially when you consider what it is that we're going to be storing, right? So we're really just going to be storing the query, which will be up to 280 characters at the most. Then we'll store some of the prediction results. The key thing is actually just storing the query itself, because in the long run, we would want to have some sort of way of labeling all of these queries. And again, in the future, that's something that we're not going to be covering in this one. So now what we want to do is sign up for a DataStax account. So go to this link right here and sign up for your account. Now, if you already have a DataStax account, that's fine. But we're going to sign up and then log into the console, something like this. So the first step that I want to do with DataStax is getting my API keys. So go into your organization settings, go down to token management, and we're going to go ahead and generate a new role for an admin user. Okay, so I'm going to go ahead and grab the client ID, and I'm going to jump into my environment variables here. And I'll just call this AstraDB client ID. Paste that one in, and then AstraDB client secret will be equal to the other one. Okay, so those are the only environment variables I'll need at this point. Now, I will be doing more things with the DataStax AstraDB. I'll do that later. For now, I want to actually allow for my application to even have that configuration. So the next part of this is to just allow in some additional configuration. So instead of our app, we'll go ahead and do config.py. And what I want here is I want the environment variables to work in my project. So os.environ. Now, what we saw before when we did that pipeline is I did the .env load env thing, right? So I did from .env import load env. Now, we do something very similar to this, but we actually do it using Pydantic. So from Pydantic, import base settings. So Pydantic is going to be installed by default with FastAPI because it's really how you configure your settings for FastAPI. That includes things that are like environment variables, so any of these things in here, but it also includes things like other kinds of configuration you might want on your entire project, like whether or not it's in quote unquote debug mode. So let's go ahead and create our base settings. So it's just class settings and it's base settings. And now we want to have our DB client ID. Okay. And I'm going to set that equal to a string, and then, or the type is going to be a string, and then DB client secret. Okay. So these are the values that I want my environment variables to be known as. So the idea here is we are going to go ahead and initialize a method called getSettings. And this is going to return an instance of this settings class. Okay. And I want this to automatically be set, automatically be configured. Certainly a little bit different than our machine learning model where we did a data class and configured all of the stuff ourselves. The actual base settings class from Pydantic will do the configuration for us based off of our environment variables. So the first thing I want to do for that is say class config and say env file equals to .env. Again, using that .env file in order for us to actually load in these values. So in the case of the DB client ID, we want it to be mapped to the environment variable of this, right? And that's actually pretty simple to do. We come in here and say field, and then we set this equal to field. And if we do ... that means it's a required version. And then we can say env equals to that environment variable field name. So another way to do this is just to say AstraDB client ID and not have a field in there at all. That will map, even with the lowercase values, to the uppercase values. But I'm going to stick with this because this is actually what I did in a different series. But the idea here is we're just going to use the environment variables for those two items. Cool. So now that we've got that, let's actually import one more thing. So we'll do from func tools, not tools, but tools. We're going to import LRU cache. And we'll wrap this here. So what this decorator does is it caches the results of this function anywhere it's called. So after it's called one time in a running application, we can call it again and it won't recreate a new instance of that. It just makes things a little bit more efficient. Okay, so now that we've got this, we can go into main.py and we can import it. So config and ml like that. And now I can do settings equals to config.getSettings. Okay, so down here, what I just want to do is say db client ID is equal to settings.db client ID. Just to verify that's installed, let's make sure our app is still running. Looks like everything is good. I'll go into my home page here and there it is. Great. So the question is, can I use OS environment anymore? Like, let's go ahead and see. So if we do import OS, and then we grab one of these environment variables. So I'll go ahead and just come in here and say env os.environ.get that environment variable. Let's take a look. And let's make sure we save it. Refresh in here. Looks like maybe I've got an error or something because it's not refreshing. Let's reload it manually and just give it a moment. It's not loading. Okay, so that is the only way we're going to grab environment variables inside of FastAPI. Okay, is using that Pydantic settings model just like that. Okay, so this is going to be important for future steps with integrating the AstraDB with our project here. Okay, so now that we have our settings all set up, we can absolutely add the AWS access key ID. So let's go ahead and do that, as well as the secret access key. I'm going to set these to be none for now, and I'll put these all lowercase. Just so we can see it in action. So settings .aws secret access key. We refresh in here, make sure everything's all saved up, and there we go. Okay, there. So it maps out just fine. Great. So now our project is ready to actually start integrating the Cassandra database, the AstraDB managed Cassandra database. Let's go ahead and do that in the next one. All right, so jump into the Astra DataStax console and go ahead and create a database. I'm going to name this one AI as an API, and the key space name I'll use is spam inferences. Now, key space is just essentially a collection of tables that you'll end up using The database name itself is a collection of key spaces, which then is a collection of tables. Next, we're going to go ahead and select a provider and region. In our case, we're going to be using AWS North America, and I'll just use the Oregon region. The region that you end up using and the service that you end up using doesn't actually matter that much. The managed database service from DataStax is great no matter what region or what service you end up using. And we don't actually have any access to those things in those services, right? It's just kind of pick which one you like, basically. So I'm going to go ahead and create a database. Now, there probably is a more serious reason when you start getting into much higher levels of production, then perhaps you will start using a different service accordingly. But that's outside the context of what we're trying to do here. Okay, so now that I've got this, I have my actual database, right? It's full on ready. So what I want to do is I want to click on Connect, and I want to navigate to the Python driver here. So we're going to be downloading this secure bundle. Now, we're going to be using the Cassandra driver, as it says in the documentation here. The main thing about this Cassandra driver is it comes with this bundle. This actually presents a problem for us when we go into production. A problem we will certainly solve, but a problem nonetheless, because this secure bundle, well, we don't want it out everywhere, but I still need to move it around. So this might be the same sort of challenge that we have with respect to our models. Like perhaps we use an object storage for this. Well, we'll see what we do when we get into production later. But for now, what I'm going to do is I'm going to create a folder in here, and I'm going to start it out with simply ignored. Okay, so the reason I'm having it called ignored is because inside of my getignore file here, I want to just go ahead and make sure that I have ignored as a part of my getignore, right? So that when I actually bring in the bundle that I just downloaded, it will be ignored from the get-go. Okay, so now that I've got that, I'm going to go ahead and open up my downloads. So into my downloads here, and I'm going to grab this bundle. Okay, and so what I like to do is rename this to something a little bit more generic in terms of Connect. Okay, so in my case, I'm going to actually make it a little bit more specific, and I'll call it AstraDB Connect. That way I can for sure have this being recognized as my AstraDB connection bundle. Okay, and so now inside of my app, I'm going to go ahead and also make a db.py. Okay, so the goal of this is to make a way to connect to any given session and cluster inside of AstraDB. But before I do that, let's go ahead and make sure in my requirements, I do have Cassandra driver there. And in my virtual environment, it actually is in there as well, because that is certainly a requirement to storing this inference data right there. Cool. Sure enough, it is. And now going back into db.py, we're going to go ahead and do a number of things related to this. First and foremost, I'm going to go ahead and import my settings. So from config, we're going to go ahead and say settings equals to config.get settings. Now, the reason for this is for our environment variable keys. Now, I'm actually going to stick with naming the environment variable keys as I have from the settings themselves, right? So settings is equal to this .db client ID and the DB client secret. Okay, so we definitely don't have to leave it like this, but I like doing this so it's very clear in this documentation that I'm using AstraDB, right? That's it. Okay, the next thing is we need to get the path to that ignored file, the connection file, the connection bundle. This is critical for actually integrating the driver itself. So we'll go ahead and import pathlib. And I want to get the base directory. So baster in this case is going to be pathlib.path of this file. And then we are going to go ahead and resolve it and then just do .parent. Okay, so that should give us the parent app itself. We will test that out shortly. Next, what we're going to do is declare the cluster bundle where it is. So cluster bundle. And that equals to, well, the string of base dir, then ignored, and then we called it AstraDB connect. AstraDB connect.zip. Okay, so we do not need to unzip this file. It will do it for us when we run our connection. That's simple enough. So next we can do a couple things. Going back into the console itself, we can actually see a few of the imports we'll need, or a couple of the imports we'll need. Okay, so I can actually bring those in to our DB, just like that, and connect to them. So these are slightly different, like how I connect is slightly different. So you see the connection here. So if I do define get cluster and paste all those things in, I have my session right there. So I'll go ahead and leave that out for a moment. But this looks close, right? So we've got our cloud config here. That's looking for a bundle. We have our bundle right there. And I did make it into a string on purpose because we do not want it to be a pathlib path. We want it to be an actual string for our cluster here. The next thing is our auth provider, right? Well, what is our auth provider? Well, the client ID, and client secret. And there's our cluster. So then I can just return our cluster here. Okay, so that of course is not a whole lot different, but it doesn't actually show me the session. So one of the things about this is we definitely need to get the session in a different manner than what we have here, right? So the reason for this has to do with how our application is going to end up working on FastAPI. So we're going to go ahead and do define get session. And what it's going to do first is cluster. And we're going to use, of course, get cluster. And then our session, we'll still use that cluster session connect thing right there. And then next, what I want to do is import something from my connection as well, from Cassandra itself. So from Cassandra.cql engine.connection or import connection. Okay, so down here in our session itself, we want to set a few things. First off, connection.register connection. This is because we are going to be using this session throughout our FastAPI application, or really wherever we need it. So I'm going to set the string of the session itself, and then session equaling to the session. This is directly from their documentation. Okay, and then finally, connection.set default connection to also being the string of that session. And then we'll go ahead and return the session. Okay, so we'll see this in a moment, but we definitely need these two things in here. That's really the key thing here. That's a little bit different than what is in the documentation because the documentation doesn't account for FastAPI. But that's the baseline configuration for our session and our cluster. Okay, so the session itself is always going to be needed when we want to execute things on our cluster. The cluster itself, well, we can actually reuse this get cluster in other places. For example, if I wanted to bring it into Jupyter Notebooks, I would use this get cluster method and then do my session call like this. I don't necessarily need in my Jupyter Notebooks to have that connection being the same as my FastAPI application. So we're probably not going to look at the Jupyter Notebooks at all in this one for using these clusters because the baseline of how we're going to store everything is actually going to be pretty simple. So let's go ahead and create our Cassandra model now. Now let's go ahead and talk about the data that we want to store and then create the Cassandra model to store that data. So if we look at these results here, we see our query. That, of course, is definitely something we want to store. In fact, this might be the only value that we want to store is the actual query that's being used in this inference model. The next part is I will actually store the inference itself or the prediction itself. So for this particular AI model, I only have two labels, right? Only two potential labels, which really means I only need to store one of them, right? So I'm only going to store the top one in this case. Now, the case could be made for storing all of this data, but I actually don't need to do that. I really only need to store one of them. And so I'm going to store the label for ham and that confidence that is associated. So that's really just 3 fields here. So let's go ahead and open up our project and go into our app itself and create a file called models.py. And so in here, we're going to go ahead and create our inference model. So it's going to be class SMS and inference. And it's going to take in another class called model. But again, let's reiterate what we're storing here: the query, the label, and the confidence, right? It's just those 3 things. And so one other aspect is I'm actually going to store a UUID field as well, which will actually be UUID.UUID1. This includes a timestamp to it, which is actually really nice. So we're going to go ahead and import UUID then. So of course we need to start building out this field, the actual model itself. So we're going to do from Cassandra and then .cql engine.models. We're going to import model. So this model class is going to be right here. And then we also need to bring in our columns. So import columns. So the documentation for the columns is, I think, pretty straightforward on what we need to do. So if you look at the documentation here, we can look for all of the fields we want. Now, remembering back to like label, for example, that is a text field. So I can look for text field like this, but really it's just simply text. It's a text column, right? And that's what it yields, text. Cool. It also allows me for some parameters in here, which is certainly something I want. So columns.text for both the label and the query. The query itself should have a max length. Remembering back to the data we had a max length for even doing the prediction itself, and that max length was 280. Now I say it should have this, but it might not have this. So I'm going to go ahead and get rid of that altogether. Now the reason that it might not have this is because, well, maybe I'm not actually, or I'm letting anyone predict anything in here. And so I'm not actually enforcing a string size of some kind where the prediction might enforce it, but the actual ingesting of it doesn't. In other words, when I'm actually creating the next data set, my query might end up being a lot bigger. I want to be able to be flexible enough at this point to do that. So the next thing is actually thinking about the index itself. So I could consider actually indexing this query. So there is some positives and negatives about this, is if this query ends up being really, really big, indexing it is probably not a great idea. If the actual query is kind of small, indexing it is, well, probably a little bit easier to deal with. I'm not going to index that at all. Instead, what I'm going to do is turn my SMS inference into just a really big data set that I'll end up dealing with later. I'm not going to be extracting anything here. I'm just really trying to get as much of that raw data as possible. Okay, so the UUID field is the next one. So we'll go ahead and go UUID. And we want to grab, we can use the time UUID or simply the UUID column. Either one actually works for us in this case. So we'll do columns.UUID. And this is going to be our primary key. You have to set a primary key. And in this case, this is what it is. Now, if you're coming from SQL, the primary key is often an integer, right? 1, 2, 3, 4, 5, and so on. Now, we don't want to do that in a Cassandra database because of how it's distributed. So it's distributed across many different machines, or potentially can be many different machines in this bigger cluster. So what a UUID field does for us is it at least identifies this particular data uniquely. Using a UUID1 is both unique and related to a timestamp. So that's what we're going to stick with. And I'll just give a default of UUID.UUID1. Okay, really simple there. Not a whole lot going on here with this model, but it will be able to store a ton of data for us. The final one is our confidence here. So we'll go ahead and do columns and then .float. Okay, so there we go. That is our inference model. So how do we actually bring this into our project? That part is actually surprisingly very simple at this point. Now that we have our database and our session set up and we have this model set up. So all we need to do is go into main. I'm going to import a few things here. So first off, we'll import models, and then above that, we'll import our database. And so in our startup method here, I need to grab my DB session. I'll go ahead and say DB session and put that equal to none. Okay, so I need to actually declare this session. So I'll use the global value again. So db session equals to db.get session. So db, of course, being the module that we just did, and that session we just created. Now again, if this wasn't written in this get session method, you would definitely want to do it in here, but I want to keep things nice and simple for me, so I'm going to leave it just like that. Next, we're going to go ahead and bring in our model, right? So the SMS inference model. So what I want to do here is just say SMS inference equals to models.SMS inference. In fact, I will do that up here because I do want to reference it in other places, not just the startup method here. And so what I'm trying to do here is I want to make sure that my database, the actual Cassandra database, has this model, the table itself. And so to do that, we're going to use a command called sync table, and we're going to go ahead and run that in here. Okay. So before we can go any further, what I did have to do, as you may recall, to our key space, right? So let's go back into our key space and take a look. We have this spam interfaces key space. We have not used that yet, right? So we didn't also declare the database itself. Now, the database itself is coming from this AstraDB connect. The key space, on the other hand, is not. So the key space is going to have to live inside of the model itself. So this is where we're going to declare it. So we'll do 2 underscores, key space, and then the key space that we just set, right? And so we can absolutely change the table name as well. I'm going to leave it in as the same table, like it's going to be named based off of the name of the model class itself. But there are other configuration options that you can have. And of course, that is all inside of the documentation for this. So if we search for table name, we can actually look in here. We've got index value here, we've got our default, whether or not a field is required, which I'm leaving all of that stuff off. But then you can also search for the actual table itself or the models themselves and change the table name as well. So a quick way to do that would be Cassandra driver Python models, and then going into the models themselves, and you can see all of the configuration for the models in here for how you might want to extend it or how you might want to change things, right? So table name and then all of that. So the other part of this is that we are really just storing one layer of data. There's not a lot of data that I need for this application anyway, but I'm not actually associating this data to any particular user. So there might be a chance that you are going to be like, oh, well, I actually want my REST API to have users. And in which case you would actually create a different kind of setup here. So I'm going to go ahead and just give a quick example of this. So I'll go ahead and say REST API user. And again, we'll still use that UUID as a potential unique identifier for them. And I also might want to have my email in here as another one. And so in this case, we could say index being our true value. Or what's better is instead of having a full-on user here, I could literally have a field in here called email and doing, something like columns.text and putting our email in there, right, as a index itself. And that would give me all of, like when I actually do query this, it would give me all of the emails that are related because of that index. Now you could do it based off of primary key too as well, but the thing about a primary key is you can only have one of them, one instance of it in the entire table, right? So this UUID is only going to work for this single one. If it was an email, then it would only be one email for all inference models. Now, if you want some more clarification on that, check out my series on scraping Amazon. We definitely implement this same sort of setup over there as well. Anyways, so back in here, now that we have the actual key space name in the model itself, I'm going to go ahead and sync the table finally, and we will be mostly done with this portion. So syncing the table is, of course, from Cassandra.cql engine.management, import sync table. And now we'll go ahead and sync that table. And I'm going to just make sure that everything's running okay. Looks like it is. And if I refresh my app, yeah, doesn't seem like I have major errors in there. I do get this warning here, this engine warning. And so the way to solve that is to go into our DB or our configuration. Let's actually go into our configuration and import OS. and just go ahead and say os.environ of that and just say 0. Or we'll go ahead and say 1. Allow schema management. Yeah, we want to allow schema management. Okay, so we refresh in here, and now that error should go away. It's a TensorFlow error, which is another one we could probably add into environment variables. Not going to worry about that right now. But instead, what I want to do is I actually want to save some data in this model, and then I want to retrieve that data. So we'll do that in a moment. All right, so now let's go ahead and actually store some of our inference data. So jumping back into main.py, down into read index, of course, we're going to go ahead and use our inference model here. And so the simple thing is to say top is equal to predict.get top. This, of course, should be a dictionary itself with the label and the confidence. So that means that my new data, the data I want to store, is going to be our query here, and then our unpacked top data. And then I'll go ahead and say my object is equal to the SMS inference dot objects dot create and unpacking that data itself. Okay. And so this I can actually return as a response, or should be able to return it as a response. So we'll go ahead and save that. We'll jump back into our project and run it. And what we'll see is, well, hopefully actual responses from hello world along with table. Yeah, there we go. And so it gives us the UUID back as well, which is nice to see, because if I do it again, the UUID should actually change. So if I refresh this, I'm seeing new UUIDs in here. And then I can also do some new queries like this is awesome, or, another one bites the dust, or, any sort of spam. This is spam, spam, spam. Who knows if that will actually even be considered spam. It is not considered spam. But if we put something like discount is our phone, some numbers in here, buy now, call now, something that's almost for sure spam, there you go. Okay, cool. So it's definitely storing this stuff, and maybe this is the response we want our users to see, maybe not. In my case, I actually do want this. I want it to just give me a label and a confidence for that label for this particular spam item, right? If it is the opposite label, of course, that could go back to that opposite label. Now, the other thing about this is perhaps we always just want the spam confidence, right? And if that's the case, then you would just have some sort of condition in here that's going to flip that around, or we could update our Preds dictionary on that. Now, that's of course not what I want to do. But what I do want to see is how do I actually turn this into list data itself? And then further, how do I actually paginate that list data? So that's something I'll do in just a moment. But I do want to see the actual responses for this. So the simplest way to get one of the responses is to just come in here and give some argument here. Let's go ahead and put it into brackets. And I'll just go ahead and say the UUID or my UUID. This turns into an argument here, and I'll go ahead and say inferences / my UUID. From there, I can get my object with SMS inference.objects.get, and the UUID is equal to my UUID that's being passed, and then I can return that object. So this is going to be read inference, right? And so granted, I can grab this recent inference right here and go into the inferences and take a look at that individual one. And what do you know? There it is. So just a really simple and easy way to save data and look at it. Like I said, I want to actually turn this into a list of data. I want to see maybe all of the objects that are in here, and I have to do that using pagination. That's what we'll do in just a moment. Now I'm going to show you two ways on how we can list out all of our data here. So the first way, I'm going to go ahead and just copy our original one, and I'll get rid of our UUID stuff, and we'll just call it inferences, get rid of that, and list this out. It's really simple. We just do .all, and that will turn this into a query set, and then we can just return a list of that query set. And of course, we can actually print out what that query set is and what it looks like in our project itself. So we'll go let that run, and then go into inferences, the actual URL for it. And what we'd see we actually see this right here. So this is showing me the CQL command that will be executed in the session. Notice it has a limit of 10,000. So we're actually going to stick with that limit and show another way to list these things out. So it does actually list everything out, and it lists out generally pretty well, and it's all in JSON data. So what I'm going to do is now take another approach that's not in JSON data, but rather streaming data. And so we'll go ahead and copy this right here. And I'm going to call this one now export. And what I want actually is my CQL query. And I'm going to set it equal to what we saw just a moment ago, this right here, right? And so this is just going to be something I will execute in my session. So a way to actually execute this data is by taking the database session itself and actually running it. So we'll go ahead and come back down here. I'll call this export inferences, or we'll just call it dataset for now. And so to actually execute this query, what we do is, well, we can say rows equals to dbSession.execute and this CQL query, and we can return back the rows there. So this may or may not work as anticipated. Let's go ahead and do our data set here. And that is just a simple way to actually execute one of the rows or some of the rows, right? And so what we see back is that data coming back in a fairly straightforward manner, right? And if we limit this number down to, like, say, I don't know, 12, it's probably going to actually respond a little bit faster. But then, of course, the actual data set is going to be quite a bit smaller once it does finishing loading. And of course, I will note that the reason it takes a while to load is because of TensorFlow, not because of the Cassandra engine itself. The Cassandra stuff is actually really fast. TensorFlow loading into memory is what takes a while. Anyway, so when we refresh this, we get, whatever this query ends up being. Okay, so for streaming data, in particular this data set, I actually want every possible row that I can up to a certain limit, which in my case, I'll leave it at 10,000, right? So that's the limit we want to use, and we want to go off of this query. So before I jump into actually how to run that query itself, I'm going to go ahead and implement a streaming response in FastAPI. So from FastAPI.responses, import a streaming response. And what this does, it allows me to call a generator and return the response or the yielded data from that generator. So for example, I'm going to go ahead and call this fetch rows, and I'm going to leave it empty for now. And I'll just go ahead and do for I in range, let's say 30. And this, I'll just go ahead and yield out a string that is basically row and I. Okay, so not that big of a deal. I'm going to get rid of that space there, and maybe row I and, I don't know, ABC. Okay, so what I can do is in this streaming response, I can actually call that fetch rows there, and it's going to call this function, which will generate all of this data, and it will turn it back into a streaming response on my actual page here. And so another thing that I could consider is actually adding / in there, which would, change how the generator comes out to where it's now closer to CSV, like a comma separated values table, right? As we see here. So what I want to do is actually turn this SQL query into having the ability to generate this same sort of data. And this takes a few steps here. So the first thing is we want to import the simple statement query from Cassandra. So from Cassandra.query, we're going to import simple statement. Okay. So this simple statement we will actually use down here in both our fetch. So we'll go ahead and do the statement. STMT is of the type statement. Okay. And then we will go ahead and come down and also add in our session here. I'll go ahead and say none. Okay. So the statement itself we want to start out with is the query right there. So statement is equal to that simple statement passing in the CQL query. And then we're going to go ahead and fetch those rows like that. Now, I also might want to also include a fetch size, like how many items in any given query should I start out with? Even if the limit is 10,000, what number of rows do I want? Like, think of it in terms of pagination. This is going to be an integer, and I'm going to set the default to being 25. Okay, so fetch size being 25, and down here I will leave it in as 25, and then I'll also include the session, the actual database session itself, which we set with db session at that global variable. Okay, so let's just go ahead and be sure to grab that with global and session. Okay, so now inside of this fetch rows statement, we can start actually building this out a little bit more. So I'm going to go ahead and separate it a little bit. And so the idea here is taking the statement itself and then adding the fetch size. All right, so updating that simple statement to the fetch size we want to use. And then what I'm going to get is my results. So RS, this is a result set is the name of it. We are going to now do session.execute and that simple statement, right? So just slightly different than what we just saw, where it takes the statement, but it also adds in the fetch size. So it's going to fetch only 25 entries at a time, but it's going to be limited to 10,000, right? So there is still that limit, that hard limit of number of data in there, because more than 10,000, it might take way too long to actually export all of this data. And so what I would offer if you need to export all of the SQL data is to probably have some sort of cron job or some sort of Celery task that will actually export the entire data set into like a CSV file or something like that, and then updating it into object storage. That's not what I'm talking about here. So now that we've got this result set, I want to just check inside of that result set if it has pages. So in other words, are there more pages in this result set? We'll just go ahead and say has more pages. Okay. So if it does have pages, it's going to do some stuff, right? So that's where our yield is going to come in. And all I need to do here is say while it has more pages, then I'm going to go ahead and run through. So for row in rs dot, or rather our results set dot and current rows. Now I'm going to go ahead and yield out the row data. Okay. So the row data is literally what's stored in our columns here. So UUID, query, label, confidence. So what we can do is this is actually considered a dictionary value right here. I'm going to leave it in with this sort of, comma separated values here. And so I'll just go ahead and use the F string substitution. So row and UUID, for example, and then comma, row, the same thing, row and label, and then confidence. Let's go ahead and just copy and paste this a couple times. So confidence, and then finally query. Okay. And so now we are going to loop through. Well, initially it's only going to loop through the first 25, right? So eventually we want it to loop through others. And so after I end up doing this, now what I want to do is see if it has more pages still, right? And so now I'll just go ahead and run this execution again. Okay, so I'm resetting the result set again. This time I'm going to go ahead and execute that same statement, but I need to add one thing to it, and that is our paging state, and that's going to be equal to our previous result set dot paging state. So this is how it's doing the pagination. Okay, so it's going to fetch all these rows and do pagination this way. This paging state is not a number, unfortunately. If it was a number, it'd be a little bit easier to implement pagination into any given actual list view itself. But unfortunately, Cassandra databases aren't as easily paginated, especially with the data we currently have, just generally speaking, how it's stored. But this is a quick and easy way to do that in terms of streaming data. Okay, and so now I don't need that trailing comma. I have all of this data. Let's go ahead and take a look. Let's refresh in here. And what I'm hoping I'll see is the actual instances and so on. And so I do. Right, so there's the UUID, there's the label, there's the confidence, and there's the query. So of course I can actually start out with a yield here as well. Let's say yield, and yielding out a string of UUID, label, confidence, and query. right? And then putting a new line there and then refreshing in here, and we can see what ends up happening with this, right? And so what we should see is basically the table header right there. And here's all this other data, right? And as you might guess, if this is too big, the request will time out and that it won't necessarily give us all of this data back, which is why I mentioned that it's probably not the most efficient in the long run for grabbing all of your data set. But it will be pretty good for a large chunk of them, which I think is actually really nice. But it's also just a way to see how we actually list out a lot of this data and also how to do some pagination with a Cassandra database. And in our case, it's just with AstraDB. So hopefully you got something out of that. I would want to test the limits here. And I'd be very curious to see some of you, if you do try to put in, like 1 million entries in here, what ends up happening? How fast will it actually respond for you? Because a part of it is, of course, the speed as to which TensorFlow is running for us. But after TensorFlow is running and my FastAPI application is set up, this actually responds pretty quick. So we will have to test this quite a bit. And I will say that, of course, if you actually go and create new data, that new data should be in here as well. And it should be streaming in there too. So if we come back into our data set here, and let's put in a few new items in there, we have all of this data, right? And so it's not going to be in order. It's definitely not going to be in order. That's what this UUID will help us do, is to know when this data happens exactly. But the way Cassandra stores data is not in order. It's stored by our primary keys, and it has eventual consistency, which means that our entire cluster of this data set will eventually have the correct data in it. So just a little tidbit about Cassandra that's in there. But anyway, so now we have a pretty cool way to at least extract a good chunk of the data that we store in our database. And yes, of course, this is what we would end up using for creating our next part of data. Like if we were actually starting to build a new data set and start labeling this data itself, right? So it does have a label, but this is an automated label. This is not necessarily something we had a human look at, which is a good and bad thing. Like perhaps we don't want people looking at all this data, because if it ends up being 1 million entries, are we really going to have people hand pick these things out? Probably not. There would be a machine learning algorithm, or there is a machine learning way to kind of separate out this data and have some of the anomalies being looked at. But really, I think the part of this is going to be also getting rid of repeated data, right? So we don't need repeated data over and over, especially when not only is the query itself the same, but also the prediction, the confidence level is the same too. So an anomaly in this case would be, well, what if the query is the same and for some reason the actual prediction is different? This would be true with the different versions of our actual model as well, like the model version that we are using, which kind of gives me to my final point with these SMS inference. Perhaps we would also want to use another item in here, let's say a text item, and we'll go ahead and say the model version and setting our default to being V1, and that's it, right? And so just another way to sort of ensure that we have the correct data in here. And of course, if I now add inference, that's already there. This is what I love about NoSQL databases, and especially Cassandra's database, is I can just add that field real fast and I'll add the data in here. Now, this won't happen to old data, right? So going back into our iteration here, if I try to get the version number here, it's only going to work for some of them, right? So what do we call it? Call it model version. So model version, and we refresh in here, the streaming data, the model version should only show up a handful of times. And actually we want to put version here too. And we get none in a lot of places, right? If not all of them. Here is version 1, the most recent one that was done, right? So that's pretty cool. Now, before we go into production, I actually want to test my AI as an API through Ngrok. Ngrok will allow me to emulate a production environment by exposing a local project to the world. So go to ngrok.com and download it. These steps, I think, are really simple. You will have to sign up with an Ngrok account. It is free. It's not like they sponsor this or anything. It's just a really easy way to expose a project to the world. And so we can test it in something like Google Colab, or really just anything that's not on our local system. So once you have it installed, you'll see that you can just run Ngrok like this. And so the command is simple. It's just Ngrok, HTTP, and then the port we have exposed. So in my case, my FastAPI port is port 8000, which I can just cancel, close it out, and see again. That's the port right there, right? So if for some reason you used a different port, you would want to update what that port would end up being, right? So again, let's just make sure it's running. There it is. And so let's give this a shot. There we go. And so what happens is it actually gives me a few different URLs here. And so if I go to one of these URLs, Ngrok will help the routing of that URL, and in a secure manner, I can actually try out my API here, right? And so this is actually emulating a production environment. So if I do hello world, I see all of that data. And then also if I look at my recently created data set, it's going to go ahead, not data sets, but rather data set. It will give me and stream out that data for me as well. Now, the reason I'm not zoomed into it is just really to test it out itself, but it certainly is working in a very similar fashion. So yet again, I can use this inside of Google Colab. So I'm going to go ahead and create a new notebook, and we're just going to call this our spam SMS requests. So that means I'm going to go ahead and import requests, the Python request module. And what I want to do is I just want to use my URL. So endpoint being HTTP, whatever that was. And then I'll just put a Q equaling to this is my query. And then I'll do R equals to request.get, that endpoint, and then print out r.json. Okay, and there we go. It now gives me that score. We now have an almost production version of our AI as an API. Now, getting this into production is not trivial, but it is something that we will look into. Okay, so the other part of this is, what about that dataset thing? So if I come in here and do dataset, right? Let's take a look at that. If I print R, we get we don't get the value that we necessarily want. Let's go ahead and do text. Okay, and so there we go. It's giving us back this text data as well. Now, a better example of this would be to change it just slightly. So instead of it being just request.get, it'll be a S, which is request.session. And then from here, we'll go ahead and say R equals to S.get, that endpoint, and then stream is true. And then we'll go ahead and say for line in R.iter lines. Then we'll go ahead and print out that line. Actually, we might want to have a condition here and say if line, and then print out that line. Okay. And so this will actually get the streaming data coming right back too. Now it's actually really fast, right? This is not that surprising. I mentioned before that the reason it seems like it's going slow on our system only has to do with the fact that I keep on saving my Python files, which ends up changing a lot of that data. Okay, so with this in mind, I do want to change one thing about my actual, inference results, and that is the method that we are using to get a proper inference. That's this right here, right? So I don't actually want to get this with get. I want it to be post, all right? So let's call this create inference. The reason I'm changing it to being create is because I actually do touch a database here. I think in general, if you're going to touch the database, turn it into a post method, because that is the method that we are going to want to use in general when we are creating data. And so now I'm going to go ahead and just leave it the index itself. We'll just go ahead and call this like hello world. Okay. And also now the query set itself, or the queue that's coming through, we will have to update this, of course, the way we actually request it. So let's go back up to our data here. This is no longer get, but rather post. And the data itself is going to be, we want to go ahead and put in queue. And this is my new query. Notice it actually still worked this time, still with that post data and the queue here. Let's go ahead and try it with the actual data in there. This time it said hello world. What if we put it in as JSON? This time it says hello world still. So it's actually not getting the correct data coming through from our post data, right? It's actually using the query parameters from our URL. And so the way to solve this issue is by coming in to our project again and adding in a schema. So schema.py. What we want to do here is we want to use Pydantic. So we'll go ahead and do from Pydantic, import base model. And I'll give this a class of simply a inference query, or we could just call it query because that's really all it's ever going to be. And in this case, I want to actually add in Q being a string, and that's it. That's literally the only thing I need from this model. So back into main, we'll go ahead and import the schema. And inside of our read index, or rather our create inference file here, instead of it being optional, it's going to go ahead and be Q is going to be related to that query. But really, this is going to be query is related to that query. And now our actual query itself is just simply q.query. Okay, so let's go ahead and try that now. We run this in here, and it will take a moment for this to boot up because I make some changes on my local project. So Ngrok also has to wait for those changes to occur. And it's certainly possible that we have an error somewhere in here. Oh yeah, query is not defined. Yeah, there's our error. This should be schema.query. Okay, and this should be, reverse that, query.q. Okay, so now it's reloaded. And I think we got it. Q is not defined. That's going to be query.q here. Okay, and let's try this again. Running back, and it looks like our system is being built up just fine. And there we go. We got our post request coming through, and this is my new query. And now if I leave that out, let's just put empty JSON, it's going to say the queue is required, right? So queue being anything I need to query. Okay, cool. So now it's a little bit more of a secure value here. Now, of course, one of the other things is that we'll probably add in when we go into production is proper headers to ensure that when we are doing post data to this endpoint, we have at least somewhat of uniquely identifiable headers for our endpoints to be run. And we'll still flush that out using Ngrok in the future as well. But I just wanted to quickly just change the way that endpoint was working. The other way is not wrong per se, but it is, well, just not very good practice when it comes to building web applications in a secure manner. And even where we're at now, we definitely want to have some sort of authentication for our users as well. Anyways, that's it for this one. Let's go ahead and thanks so much for watching. Hopefully you got a lot out of this one. Now in part 2, what we need to do is actually deploy this application into production. Now it's a little bit different than a standard Python web application because of our machine learning model. There's a number of things that we have to consider to make sure that that is running into production as well. So we're going to cover all of that, and we're going to be deploying from scratch on a virtual machine so that anyone in the world can use this application. Now, sure, we used Ngrok as a test to deploy it to the world, but actually getting it on a production server is what it's all about. So be sure to subscribe and hit that bell icon to be notified when I release that one. But again, thanks so much for watching. My name is Justin Mitchell. Look forward to seeing you guys next time.